less than R, less than C.
Don't know
We're
where
in
I
this
saw it
first
before.
voided region.
Maybe I'm thinking
Our inner
I saw it on the
shell
answer sheet. 85.
has a total charge
523.
of
Is that
plus
what I wrote?
2Q. And so that is
Yep.
what would be Q enclosed here. So Q enclosed is plus 2Q. So that means that the electric field can be written as a point charge in terms of epsilon or just as K. Writing it
Welcome to
like
the channel.
that, we
Here we
get
tackle complex
1
questions and
divided
break
by 4
them
pi
down into simple
epsilon
step-by-step
0
solution. Let's solve
times the total
today's
charge
problems together.
inside, which is 2Q.
Okay,
divided by
this
R
problem, regardless of what you learned in
There we go.
from this book, this is a simple
And let's see
extension
now.
of the Pythagorean
C less than R
theorem
less than B.
here.
So now we're in this outer region.
So
Okay.
I'm just gonna write.
So if we're in this
Welcome
outer
to the
region,
channel.
I know
Here we
that
tackle
electric
complex
field
questions
must
and break
be
them
equal to
square
0
root
simple
here in this
step-by-step
of
solution.
because
Let's
when we're
four
solve
squared
today's
conductor,
problems
the
together.
electric field,
plus
net electric
2
field must be
squared.
0.
Okay, this
At
problem,
plus 2Q here.
regardless
So
of
we
what
need
you
1
learned
minus
in,
2Q
and
on
I'm
this
just
inner
gonna solve it for
surface.
Z. This is a
But in general,
simple
E
extension
still
of the
must be
Pythagorean
equal
theorem.
to
It's going to
0
be the
here.
square root.
Because we are inside of the
So I'm
conductor.
just going to write
And finally, when we are
8
Welcome to the channel.
outside
Here we tackle
8
this
squared
complex
system,
total
questions and
length
break
or
them
the
all you have to
square
do is
root
take total charge
step
of
by step
4Q plus
solution.
2Q is
Let's
equal to
solve
4
Q.
today's
squared,
problems
which
So
is
together.
16 minus 2 squared, which is 4.
Okay,
This
E
problem is
equals
going to be
1
regardless of what
divided
you
by
learned
4
in
pi
I'm just going to solve it for Z.
times
This is a
minus
simple
2Q
meter extension of the
over
Pythagorean
R.
theorem.
The
answer
answer?
square root. So I'm just going to
Easiest
write
question of this unit so
Welcome
far.
to the channel.
Alright.
Here we tackle
8
complex
squared
questions
total
go ahead and
and
grab
length or
break
the
them
this.
square
down into
root
simple
And what do we see?
step-by-step
0,
solution.
0. So
minus
solve today's
squared,
problems
which is
together.
16 minus 2 squared, which is 4.
0 there.
This problem is going to be regardless of what you learned in I'm just going to solve it for Z. This is a simple meter extension of the
Easiest question of this unit. The answer?
square root. So I'm just going to
Easiest
write
question of this unit so far.
8 squared total square root square root minus squared minus 2 squared minus 4. This problem is going to be square root meter extension of the Pythagorean theorem.
The answer is square root of this unit so
dot is. So this guy must be 0. What about on the outer surface? Outer surface must be the total charge on this shell.
Welcome to EDU Workspace.
So in this example, we have an inner shell with a positive 2q charge and an outer shell with minus 4 charge, and we're going to find the electric field. So to begin, we need to write down Gauss's law. Clothesline integral, closed loop integral,
Looks like they did
divided by
multiply that out.
Also remember that when we can see that the electric field equals kq, total charge inside divided by k is just a constant in our terms into the noun. You can also write it in terms of Planck's law, and it is 1 divided by 4 pi epsilon. Okay, so let's find the electric field. Alright, so right at this principle, on the inside of this square shell, there is no charge here. If there is no charge, then Q is the most of the electric What about in between our first shell, A to B? Remember that in a conductor, so begins to be sine. So the electric on inside will be reduced to B must
Sine squared of 5 plus sine squared of 5.
B less than or less than C, we're going to support the region. Our inner shell has a total charge of plus 2q, and so that is what the Q equals here. So Q equals is plus 2q. So that means that the electric field can be written as a total charge in terms of, okay, so just as writing it down, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2q.
Alright, so
divided by
is question number 39.
And let's see now. Let's see
39
what's
is really only
this region. Okay. So for this outer region, I know that the electric field must be equal to 0 here because when we're in a conductor,
And we have the x and y direction.
so we need minus 2q on this inner surface. But in general,
45 degrees, which by the way would make this one.
and finally, when we are outside of the system,
And then we have F2.
minus 2q, so q is minus 2q, and we get E equals inside times minus 2q over r. And let's see now. Alright,
Think about what's
we can go
going
ahead
on
and process. And we see
considering where 30 degrees is
right there.
and that's going to
C.
be
You see here. So we need 2.
2. And then we have degrees.
And now,
Okay, so
even though this is a quadratic function, you can get out your graph
here F1
and see what happens when you have a negative value and we
going to be
outside
100 times the sine of 45 degrees. That's the square root of 2 over 2 over 2. And that's
to see what happens when you have a negative sign outside
I direction. And the same thing in the J direction. And that's going to
This looks like
okay, F2. Go into Z. Well,
when you graph
X
the
direction
two
is going to be
solutions, you choose the physical solution.
cosine of 30
And so in this instance, it will be
over 2. So this is just going to be 150, whoops, negative 150 goes negative direction.
Here we go. Okay, so now we can look at the charges that are around these shells.
And
Okay,
the side
let's look at the inner surface of our
30 degrees is 1
The inner
half.
surface of our small. Remember, electric field must be 0 on the inside of this guy, where that green dot is. So, this guy must be 0.
Alright, so
We're
simplify
going on the outer surface. Outer surface must be
this
the
one
total charge
is
of the
just
shell.
going to be 100
Okay, let's look at the large one. Okay, on the inner surface, we need to have another zero, so it has to cancel the total charge of shoots in our shell. So we need negative 2 in the inner surface.
2 is going to be negative 75
And then what about on the side?
comma 75.
Okay, so now all we have to do is just okay, this is take it out. Okay, so there's a minus 2 right here. So remember it has to be all that the only way for the net charge
Two is going to be
300 newtons, just hold down.
Welcome to EDU Workspace.
Okay, so we have 2 concentric shells in a radius A. We have our inner shell, radius C, our radius D, our outer shell. The inner shell has 2 cubes, outer shell has 1 times 2 cubes. And we're going to find the other force and where the it's 5. So remember that when we have a point charge, the electric field is given by the sorting K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss law.
F2, we actually don't even have 1 degree horizontal. It's directly upwards.
It says that the closed loop integral of U dot dA
This force
equals the total charge closed divided by epsilon.
opposite directions.
Alright, so first region, radius less than
Instead
A.
of using cosine,
Okay?
because we have the 5 charge,
We are right here in this little green dot. We have no charge there. With no charge, E is 0. So E comes to 0. Okay, A less than R less than
this
B.
right here,
We're in this inner shell first, our smaller shell. This is a conductor. One of the properties is that E equals 0 times
cosine,
So, 9. B less than R less than 9. So now we're in this first one. It's also equal. Well, what is the total charge in that region? Q closed. Well, as long as just charge that inner shell. So, now we can just imagine that it's one charge and say
This time we actually do
electric field
force 2.
E equals 1 divided by 4 pi epsilon times Q. First we charge the side to Q over square. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Okay, A, well, do our Gaussian surface. We're somewhere in this inner shell. What is the total charge in here? Well, it must be 0. Why is that? Because we're inside of the conductor. So, E equals 0. There it is. That's not too bad. Now what happens if we are outside of
This time we
everything?
actually do it.
So now what happens if we are doing a Gaussian surface outside of this? So, well, what is the total charge closed? plus 2q minus 2q, that equals 0. 1, e divided by 0 here as well. We can go ahead and graph this. 0, 0, so we have these functions 0, 2q, b to c squared right here. It goes something like this, it's one over r squared. And then it goes straight back to 0 in our outer shell. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our spherical sphere charge of our small shell? So, if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. We must do that. Now, what happens if we are outside here? What about the outer? Right here. Well, what is our charge enclosed here?
This angle is actually the angle between the resultant vector and the x-axis.
The electric field due to x to q charge.
Theta here, or sorry, the angle between the x-axis and force 1 is 10 degrees.
What about our large shell? We go right on this inner diameter. Okay, we know that the electric field must be directed here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land at the surface. Well, minus 2q. Then what about this outer surface?
This angle is actually the angle.
We have a net charge vector right here. Well, what is our charge enclosed here?
This angle is actually
So, the outer
force 1 is 10 degrees.
must equal to charge.
Theta here, or sorry, the angle between the x-axis and force 1 is 10 degrees.
What about our large shell? We go right on this inner diameter. We know that the electric field must be directed here. That means it needs to cancel plus 2q that's happening right here. That means all of the minus.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going in the test. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of E dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So, in general, this is our Gauss's law. And this is our area element. This is the total charge enclosed in our Gaussian surface. There's epsilon 0, just a constant. And E is what we're looking for. So let's look for our first region, which is when we have a radius less than A. So for, or less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0. So let's go ahead and look for the electric field everywhere. So in order to find the electric field, we're going to write down Gauss's law of this region. Alright, what about if we are in between A and B as a line and a shell right here? Well, if it is a conducting shell, total charge, then by definition, divided by, it must have 0 electric field. So in general, this is our Gauss's law. So we have the same thing. And E must equal 0 here. This is the total charge enclosed in our Gaussian surface. Epsilon 0, just a constant. Now what about this cavity between B and C, which is so for B less than R, less than C, or less than A. Well, now we do have some charge, and we have the total charge on this shell, plus 2Q. So, just in general, we know that the formula for the electric field of a point charge, E, equals K, which is 1 over 4 pi epsilon, or 99, KQ, well, divided by R squared, and by definition. We can use this for our region between B and C, and we see that the electric field E equals K Q, which is 2Q. Q right here is the total charge divided by R squared. R squared, so, is just B's. We can write this more explicitly. 1 divided by 4 pi epsilon, total charge on this shell, plus 2Q. So, times 2Q, just in general, we know that the formula for our electric field point charge. Okay. Now, what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor. So, for the region between C, less than R, less than D, E equals 0. Okay, we're inside that conductor. Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just use this formula right here for our regular point charge, and we get an electric field E, C, and D. So now equals 1 divided by 4 pi. Remember that the electric field epsilon 0 times 6Q, so for the region over R squared. C, R G, 6, E, 0. So there we go. Those are all of our regions. Now we can go ahead and graph this. And then finally, what about... So if we wanted to graph it over something like this, so we have R, and we have E, and we have, well, when R is A, D, then we have B, which is C, Q, plus 2Q, D, so we'll just use this formula right here for A, and we are going to get between regions A and B, E, C, and what about between C and D? 1, originally 0 because we have no charge, times inside of that inner shell. And between regions B and C, here's our formula. So it goes as a 1 over R squared. So something like this. Those are all of our regions now. And we see a similar function for when R is greater than D. However, this time we are going to have a different U factor in front, and it's going to be a little steeper like that. And so that's that. Now, what about the charges on the inner surfaces? And what about between C and D? Well, okay, so the inner surface, what is the total charge on the inner surface side of that shell? Well, and it has to be 0. Why is that? Because the electric field is 0 on when we have a Gaussian surface right here. So this guy is 0. Something like this, and a Gaussian surface. You can't have any charge right there. There's nothing on the inside. We see a similar function. So inner. However, this time we are going to have a different front, inner is 0. And I guess we can call this state. Okay, what about the outer? Now, what about all the outer surface right here needs to contain all the charge for this inner shell. So it has to be plus 2Q. The inner surface, what is the total charge on the inner surface? Okay. And what about for our law ratio? It has to be 0. Why is that? Because the squared electric field is 0. When we have a Gaussian surface, this guy. Okay, the inside to the inner. So we do the Gaussian surface right here. We know that we must have a net 0 electric field. The only way for that to happen is that there must be an induced negative 2Q charge on the inside right here. So it has to be negative 2Q. Why is that? Because E needs to be net T equals 0. Okay? For this inner shell. So now the outer surface. So our Gaussian surface. Okay? And what about, that's just the total charge for these two. And that's that. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be, taller than this. This is 6 divided by 4 pi, and this is 2 divided by 4. The only way for that to happen is that there must be a to check heat charge and that's that. Okay.
I1 is V1 divided by Z1 multiplied by V1 is equal to V2 divided by Z2.
Welcome to EDU World Space.
V2 is impedance, and then here Z1 divided by Z2 is equal to
also
V1 divided by V2.
Is that this is, and we were to have units on this,
and 1 divided by
expect this
and 1 divided by 2 all
taller
is equal to Z1 divided by 4 times Z2. Right, and further, and 1 divided by 2 is equal to I1 square root 2 and Z1 divided by that is and only divided by. So solution is obtained with the given value for the incident V2 divided by. So and 1 divided by 2 that is equal to square divided by that is
Welcome to
divided by
EDU
8
World Space.
and 1 divided by 2 is equal to 10 times divided by 10. And 1 divided by 1 divided by and 1 divided by and 1 divided by and 1 divided
All of these forces so it's a halfway. Hold it for 15 degrees in y-axis and 75 side equals 7. Is equal to 10 times both sides. In the opposite direction, 2.5. that's F1. F2. The y-axis. Finally, for forced loop, along the positive x-axis, there's no vertical. So to the right, 6 dots. Don't know anything else. So, let's simply start summing up all of our process with our y. Here we go to is force 3. Pretty much just say that process over 47.6.
I don't know, so far this section seems to be exactly the same as the previous section. Don't know what is different, seriously. So, we're shown that this is 30 degrees. We're also shown that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because in all it's a right angle.
Welcome to EDU World
The
Space.
magnitude and direction of the resultant force. Well, force resultant in the x direction is going to be 400, because I don't 30 plus 800 cosine 45. Force resultant in the y direction is going to be 400 sine 30 minus 800 sine 45. The resultant force is going to be the square root of FRX squared plus F magnitude y squared, and the angle is going to be the inverse tangent
Welcome
of
to EDU
x
World
direction y over FR. Let's put all of these into a calculator. It's important that you do the first two so that you know exactly where that theta is, whether it's downward or upward going horizontal. And so, going to a calculator, force resultant in the y direction is going to 400 cosine 30 plus 800 resultant force 5 square root 912 x sine Okay, next result, force is going to be 400 sine 30 minus 800 sine 45. Y squared negative 366. First two. Exactly where square root downward or upward the first one and first two. Know exactly where squared plus second one 400 and squared is 983. 400 and theta is inverse tangent of the second one, or the y direction, negative 366 over the x direction, square root negative 22. 21.8 degrees. So we're supposed to measure clockwise from the x-axis, so that would be those two are my answers. Let's check. And the book 983, 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction. Alright,
Welcome to EDU
really
World
a
Space.
continuation, although this is simpler than problem 63. I do have my coordinates vectors, which is this. This one's going to be in the I direction, this will be in the J direction, and this will be in the K direction. So we're supposed to measure. So I need to express each as a Cartesian vector. I'm going to create some room here by erasing a lot of this stuff down below. Alright, this is really a continuation, although this is simpler than problem 63. Easier said than done. I do have my coordinates. Alright, this is really a continuation, although this is simpler than problem there. Sweet. Okay. I'd also like to do this. I direction. J direction, vectors, and mouse direction. Okay, so F1 is I 80 cosine 30 cosine 40. So let me get what that amounts to. That's 53.1. That one. Sine 40 at the end. It's going to be 44.5. And then 80 sine 30. Which is going to be 40. Okay. So, F1 would be, F1 is 53.1 I. And that is in the positive x direction. In the j direction, I'm going to look at the book because drawing's better than my silly drawing. That's that one. Sine is good. Minus 44.5j is going in the negative y direction. And then it's going to the positive k direction. And then f sub 2 is just going to be 130. That's it. And that is in the positive x direction. 53.1 in the j direction.
Which is F1 and 2 and F3.
And that is in the positive x direction.
Resultant force. That's measured from this x plane. So we actually have the magnitude of this force is actually to find the sun. The horizontal coordinates. There's 300 newtons. We're just told that. We're also told that the angular force per x-axis is 10 degrees. So this angle right here is 10 degrees. And this angle right here is 6 degrees. So total forms a 70 degree angle. 20 degree angle. Product axis, which is 20 degrees. On the other side, we have force 2 of 200 newtons. It's just straight vertical on the x-axis. Third force is 100 newtons. 5, 12, 13 showing resultant force. So the negative x-axis is 5, 12, 13. So regarding the sun, all of our x horizontal coordinates for F1 is something 300 newtons. 300 times cosine, cosine on this cosine responds to x or horizontal. For F2, we actually already have the horizontal coordinates, and it's directly upwards. For F3, however, it's subtracting because this force is going in the other direction.
Welcome to EDU World Space.
That's force 1.
So in this question we have been
Instead of using cosine, because we have a 5, 12, 13 triangle, we just use trigonometry for right triangles. So for SOHCAHTOA, in this case, cosine adjacent over the hypotenuse.
X in the y direction is equal to 550.
This right here gives us r.
And the square root equals to negative 650 into 10 raised to 5 into the square. Right, and then fixing in the speed direction is easy because it is in the other direction, right? Now we are going to use the measures theory, right? And
This time we actually do
for that we are going to go to the circle and put that in the x's and we're going to welcome to the right? So in this we have to say that it is taking red value of right? So that is how much we want right to do this, right? right, and you calculate it together equal to 425 into 10 raised to 1. Right now, all we need to do is that we need to find out the gradient of the circle, and we have the expression for the radius as well, right? And we have underneath the difference of the strains divided by 2, so it's just plus shear strain divided by 2 whole square. You have the value, you just plug them in, and you get that equal to 2.4 and 2.8. That to 1 into 10 raised to power negative 4, right, and that is approximately equal to 3.82 into 10 raised to power negative 6. Right, now what we need to do is that we need to graph the circle. Right, so let's take a look at that. So now as you can see over here that this is the point C at which the state of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right? Because we take the help of the circle. Now for that, principal strain is equal to 4.7% off, right? So you have the value, you just plug one and you get that equal to 57.8.
Here, or the angle between the x-coordinate axis
and the other principal strain is also plus r, right? Again, you have the value, just plug them in, and you have the value. You also in your time, right? You have 773 into 10 raised to power negative 6. Right, now that we have the value of the principal strain, we need to find out the maximum in plane shear strain, right? That is given by this right? So divided by 2 and equal to r. Right, so when we flip this to over here,
in this problem, first I just draw the free body diagram. Now, here theta is the angle made by the force F with the horizontal in the anti-clockwise direction, and FR is the resultant force. And phi is the inclination of resultant force with positive x-axis in the counterclockwise direction, and alpha is the angle made by the resultant force with negative x-axis. Now I will apply the law of cosine, the vector triangle, and the expression for OA square is equal to AB square plus OB square minus 2 multiplication AB multiplication OB cos angle ABO. Or in this problem, you can write the next equation as diagram, or OA is equal to under AB square plus OB square minus AB multiplication OB multiplication cos angle ABO. Finally, you can write the value of FR as under 450 square plus 700 square minus 2 multiplication 450 multiplication 700 multiplication cos 45 degree square. So you will get the value of FR as 497 Newton. This is the magnitude of the result. Now applying sine rule to the vector triangle, so I can write AB square plus OA by using the sine angle AB cos O equal to AB by sine angle AOB, or FR by sine angle ABO is equal to 450 by sine angle substituting the values, so you can write 497 by sine 45 degree is equal to 450 by sine 15 degree plus alpha, or 15 degree plus alpha is equal to sine inverse 450 by 497 multiplication sine 45 degree sine. So finally you can write the value of alpha as 39.81 degree minus 15 degree, which is approximately equal to 25 degree. Pi angle is equal to 180 degree minus alpha, which is equal to 180 degree minus 25 degree sine. So you will get this value as 155 degree. The inclination of resultant force with positive x-axis in counterclockwise direction is 155 degree. Sine inverse.
Welcome to EDU World Space.
Question 47.
In this question,
Oh, it's the same question. So this time we're told that F sub B is 600 newtons and theta is 20 degrees. This is the same question but actually easier. Because it's kind of like we're working forwards on this one. Given basically everything we need to know. It's the same question. Straightforward one, I guess is the point. Magnitude and direction of the result. So, F R X is going to be 700 sine 30 minus 600 degrees. This is the same question. Is it 20 degrees? It's 20 degrees. Cosine 20 is 20 degrees. F R Y is add them both together. 700 cosine 30 plus 600 sine 20. 600 sine, yep. FR is the square root of FRX squared plus FRY squared. So let's just put those into the calculator. In parentheses, 700 sine 30 minus 600 cosine 20 and squared. In parentheses, 700 cosine 30 plus 600 sine 20 and square. 839 newtons. Now this is question 47, and that is the correct answer. Now, inverse tangent. So let's just put those in the calculator. Of the y value over the x value. 700 sine 30 that in the calculator cosine 20 and squared.
Right.
700 sine 30 minus 600 cosine 20 squared. Copying and pasting from the other equation and squared. 700 sine 30. See how am I measuring this? Counterclockwise. This is from the positive y axis. Interesting. You think about what's going on here. FRX is negative 213. FRY here, so the theta that I measured is this, that I calculated is that, and that theta was 75 degrees. It's negative, but it means that, 75 degrees. So if we're going to measure it counterclockwise from the positive y-axis, and that's going to make it there. So that's just going to be 15 degrees. And that is correct.
Welcome to eating
So,
your space.
the resultant's going to be here, 15 degrees. I've been calculating that, and that theta was 75 degrees. The result is this, y calculated that, and that theta was 5 degrees. And that's going to be negative. That's just going to be degrees. We're going to measure it counterclockwise from the positive y, and that is correct.
So what we're going to do now is
So that's just going to be and that is correct.
right here we work over here, right? And just to take care of the exam angle. I think that will be most problem. Now we'll be able to build a right after what is the value right now we also use right, and that's
Right angle here.
Difference of
Here.
plus
This is 40.
right, so this is how right, and that is fine. Right, now all we need to do is that draw circle.
F1 is just the negative F2. We're going to have a that's why plane is going to be F2 30 degrees.
So I should
F2 in the next direction. then we need to add that to F3. Result is positive y-axis. Alright, so F1x
For that, you have to
F2x
gamma
I'm just going to remember that I narrowed this for the answer negative. Okay, so as F3 going to equal F1 opposite.
Right now, first of all, we have to same sign, right? The reaction mechanism would be
600.
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field everywhere. So, to begin, we need to write down Gauss's law. Clothesline integral equals loop integral and dA equals the total charge inside divided by S. Also remember that when we have a charge, we can say that the electric field equals kq, total charge inside divided by r squared.
So,
K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, divided by 4 by epsilon. Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this little shell. There is no charge here. If there is no charge, then Q is 0, so the electric field is also F2 equal to 0. What about in between our first and shell, A to B? In a conductor, the total electric field must be 0. So, there's no charge on the inside, so we reduce B must less than 0. B less than or less than C, when it is first ordered region. Our inner shell has a total charge of plus 2q, and so that is what the Q includes here. So Q enclosed, you can also write this as 2q. So that means that the electric field can be written as a point charge in terms of epsilon, so just as minus we get 1 divided by 4 epsilon 0 times the total charge inside, which is 2q, divided by r squared. And let's see now. C less than R less than D, so now we're in this outer region. Okay. So in this outer region, I know that the electric field must be equal to 0 and here is 0. Because when we're in a conductor, the electric field must be 0 plus 2q here. So we need minus 2q on this inner surface. But in general, E still must be equal to 0 there because we're inside the conductor. And finally, when we are outside of the system, all you have to do is take the total charge minus 4q plus 2q is minus 2q. So Q enclosed is minus 2q. And we get E equals inside divided by epsilon times minus 2q over r squared. And let's see now. Alright. We can go ahead and graph this. And what do we see? 0, 0. That makes sense. 0 there. Between B and C, we see
Determine the magnitude and the direction of that we're saying it is. Now I need the magnitude of that. Square root of.
And now we have to remember one of the properties. So even though that this is a quadratic function, you can get out your graph.
So let me put that.
And see what happens when we have a negative value outside times minus your expression that you're looking at. So I'm graphing it now, and I think that all of you should graph it as well. To see what happens when we have a negative sign outside the expression. It looks like we need to do something like this.
Square root 420.
Now more, excuse me. When you graph it, there will be two solutions. And we choose this physical solution. And so in this instance, it will be
28. Very good. Okay, so now
outside. Alright, there we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0. There's nothing on the very inside of this guy, where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell, plus 2q. Okay, let's look at the large one. Okay, on the inner surface, we need to have an electric field 0, so it has to cancel the total charge from this inner shell. So we need a negative 2q in that inner surface. Okay? And then what about on the outer surface? Alright, well, here we go.
First one's going to be
On the outer surface, all the degrees in these shells.
second one.
Think about, okay, well there's minus 2q right here. Remember, it has to be out there.
Y in there. 20
Minus 2q.
degrees.
So,
Third
that's
one.
the only way for the net charge to be like outer surface must be the total charge to be 2.
And again, I'll check this out.
Okay, on the inner surface, we need to have the total charge from this inner shell. So we need
This force on the left side, this is 1. This force on the 2. And the force on the right side.
Welcome to EDU World Space.
Okay, so we have two concentric shells, and a radius A, a radius B of our inner shell, and a radius C, our radius D of the outer shell. The inner shell has a total charge of plus 2q, the outer shell has a total charge of minus 2q, and we're going to find the electric field everywhere, and where the charge is. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is.
All these forces were summed
Welcome to EDU Workspace.
Says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon.
Write out all of our
Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell, first our smaller shell. This is a conductor. One of the properties is that E equals 0 inside of conductor. So, E equals 0. B less than R is less than C. So now we're in this first orbit. It's also equal. Well, what is the total charge in that region? Q enclosed. Well, it's just charges out of your shell. It's 2Q. So, now we can just imagine that it's a point charge and say that the electric field E equals 1 divided by E dot dA 4 pi epsilon times Q, total charge inside is plus 2Q over R squared. We are here in this little green dot. You have no charge there. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Okay, A less than R less than the surface for somewhere in here in our shell. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So, E equals 0. There it is. Almost not too bad. Now what happens if we are outside of that region? So now what happens if we are doing a Gaussian surface outside of this system? So, well, what is the total charge enclosed? Plus 2Q minus 2Q, that equals 0. 1, E divided equals 0 here as well. We can go ahead and graph this. 0, 0. So we have these regions 0, 2Q. B to C, right here. Goes something like this. It's 1 squared. And then it goes straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, of our smaller shell? So, if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. Now, what happens if we are outside of? What about the outer? What happens if we go right here? Well, what is our charge enclosed here? Plus 2Q minus 2Q. Plus 2Q. That's everything. Everything is in there. E. You have an electric field due to the plus 2Q charge. There it is. 0, 0. So we have these regions at 0. Plus 2Q. B to C. What about our large shell? We go right on this inner diameter. Right here. Okay, we know that the electric field must be 0 here. That means it needs to cancel with this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at this surface. Well, minus 2Q. Then what about this outer surface? It's got to be 0. We have a net charge of 0 here. Well, what is our charge here? Plus 2Q. So, the outer must equal to 0. Plus 2Q.
Next step is to find the angle of
our large shell. We go right on this
by taking the arctan.
That means it needs to cancel.
Welcome to EDU Workspace.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q. The outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B. The outer shell is bound by the radii C and D. We're looking for the electric field everywhere. and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of v dot dA equals the total charge that is enclosed in our region divided by epsilon 0.
This angle.
So in general, this is our Gauss's law, and this is our area element. This is our total charge enclosed in our Gaussian surface. This is epsilon 0, just a constant, and E is what we're in charge. So let's look for our first region, which is when we have a radius less than A. So for or less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0. So let's go ahead and look for the electric field. So, in order to find the 0 field, we're going to write down Gauss's law for this region. Alright, what about if we are in between A and B, so I'm going to show right here. Well, if it is a conducting shell, then, by definition, it must have 0 electric field. So we have the same thing.
With the y-axis,
E equals 0.
with the x-axis. Force 2 has a force of 200 newtons and it's directed
Now what about this
upwards
cavity between B and C?
Force 3 has a force
So,
of 180 newtons.
B
It forms a 512
so
Fulton triangle
C
with the negative
A.
x-axis.
So now we do have some charge. We'll have the total charge on this shell plus 2Q.
We have to
So,
actually break down all of the
just in general, we know that the formula for the electric field of point charge E equals K, which is 1 over 4 epsilon, or 99, K cubed. Well,
first force
divided by R squared. By definition, we can use this for our region of
some value J.
and we see that the electric field E equals
Force value of
K
0I because it's just straight upward, which
Q
is not even any force.
to Q right here is the total charge divided by R squared.
J.
R squared
Finally, our third force. Because it's a 512 Fulton triangle, which is a right triangle,
by epsilon.
Drag means break down all the vertical force on this force.
Over R versus
For the horizontal components,
now what about the region C and D? So now we are in this outer ring. Well, we are in this outer ring. Remember that the electric field must be 0 because it is a conductor.
purely the horizontal component will
So, for the region
here it's just
C and R D, E equals 0.
adjacent of our bodies. 12, 13.
Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than
Vertical
D?
for sine, and so that's so opposite.
Well, when R is greater than D, then we have the total charge enclosed, which is 4Q, 2Q, 6Q.
Final component.
So we just use this formula right here for our regular point charge, and we get our electric field E, C,
Cosine
equals 1 divided by 4 pi
plus
epsilon 0
sine
times 6Q, so over R squared C.
all of it to their own respective sections. So that they add up. So let's take a look at X here.
Those are all of our regions. Now we can go ahead and graph this. Finally, so if we wanted to graph it, it would look something like this. We have R and E, and we have R A, D, C, see 2D.
Except that it's the results.
So we'll just
Fourth question, whatever the results are.
okay. And we are going to get between regions A and B. And what about between C and D? 1. Originally,
58.97.
sometimes inside that inner shell. And between regions B and C,
All of our y coefficients.
so it goes as a 1 over r squared,
Y plus 2
like this, and we see a similar function for when r is equal to d. But this time,
800 times sine
we are
of
going to
30
have a different refactor in front, and it's going to be a little steep like that. And so that's that. Now, what about the charges on the
y value
surface of B?
58 times 30.
Well,
How do we know about the actual y component? Like the magnitude rather than
okay, so the inner surface, where's the total charge on the inner surface size? And it has to be 0. Why is that? Because the electric field is 0 on whenever we have a Gaussian surface right here. So this guy is 0. Surface, and the charge right there, there's one on the inside. And so you see a similar function that works out inner. This time,
really quick.
inner is 0.
Fine. Let me do that.
Okay, what about the outer?
Y over x.
Well, the outer surface right here
Plug this into the calculator as well. So lots of plugging into this problem.
needs to contain all the charge for this inner shell. So, Q. Okay, and what about for our large?
So, final answers are that our force is, our F1 is 868.9 newtons, and it forms 21.3 degree angle.
So we do a Gaussian surface right here.
Or the x prime axis.
We know that we must have a net 0 electric fields.
Of course, I'm going to draw a
The only way for that to happen
diagram.
is that there must be an induced negative 2Q charge inside right here.
Here,
So this means
Plug this into the
we have a
why is that? Because we need to be net equals 0.
here.
Okay? For this inner shell. The outer surface
That's 30 degrees.
is our Gaussian surface.
But I want to put the tails together.
That's just the total charge for
Here.
this two.
This is 45 degrees. And this is the force F. So,
And that's that.
the
Also,
result
another thing to know about this
X
fact
direction
is that this is
going to be
we're to have units on this. We would expect that this would be, we know, taller. If this is 6 divided by 4 pi, this is 2.
minus 14 times the cosine 30 here
And that's that.
minus F. But I want 5 here. That will really be below. The result, of course, in the y direction is going to be 14 sine
Welcome to EDU World Space.
minus F sine 5 again. result is going to be square root of f(r) squared plus f(r)y squared. I was going to write everything in there, but then I realized so just going to leave it like this. So what I'm going to do is put this into a calculator and graph it and look for the minimum. So, square root of 8 minus 14 cosine 30 minus y, wherever I see f, is
Welcome to EDU World Space.
minus y. Cosine 5 plus and then I have to square that. Plus 14 sine 30. So what I'm going to do is minus fy sine 45. So square that. So what I'm going to do is put this into a calculator and grab it. Wait a minute. I didn't want that to be y. I wanted that to be try that again. X and X. Now it's graphing it out so I can actually see something here. There we go. Minimum. Huh. Interesting. So let's just think about. Looks like the minimum is around the y-axis. But let me just verify this. I want to look at the drawing about this. The force is probably going to be around 10 kilonewtons. So I'm going to set my x-axis to be like 0 to 10. And my y-axis is going to be the result. You know what? I'm going to set everything 0 to 10, 0 to 10. Now it's graph minimum. 0 to 10. Looks like the minimum is around the 0 minimum. There we go. Alright, now I can see the minimum. It is that now. Looks like the minimum is around the y-axis. 2.0 kilonewtons around FR. I'm going to set my x-axis to be 7.09. Probably going to be around and verify the results. I'm going to set my x-axis. You know what? I'm going to set everything to be. It actually says 2.03 and 7.87. Sure that I would get the same answer if I have two significant digits. Let's see. Yes. Alright, now I can see the minimum. Well, at least this diagram seems easier to see. A little bit harder to interpret. Let me go ahead and draw what I can draw here. Poor job of drawing that y-axis. Let's try it again. Okay. So, continue this through. We've got a point B down here, which looks like an easy one. Definitely the easy one. There's a point A up here. We were shown that this is 3. Well, at least this diagram. This is 4. This is 2. A little bit harder to see. That's it for that one. point C back here. We've got a point B down. It's harder to visualize. Okay. That's so. But the hypotenuse is 2 feet, and the angle is 20. So I'm going to green A this, and I'm going to indicate that this is 2 cosine 20 and this is 2 sine 20. And then there's like C back here. Alright, so the distance from A to B for U then the hypotenuse is going to be, in the x direction it's going 1.5 feet. But in the y direction, it's going negative. This is 2 to 3, so it's only negative 1 foot. And I'm going to indicate that in the z direction, it's going down 4 feet. And this is sine cosine.
Welcome to EDU World Space.
AC.
So in this example, we have an inner shell with positive 2q charge and an outer shell with minus 4q charge, and we're going to find the electric field everywhere.
Or in the x direction.
So to begin, we need to write down Gauss's law. Clothesline integral, closed loop integral of E dot dA equals the total charge inside divided by epsilon. Also remember that when we have a charge, we consider the electric field equals kq over inside divided by r squared. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, and that is equal to 1 divided by 4 by epsilon. Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then Q is 0, so the electric field must also be equal to 0.
Welcome to EDU World Space.
Alright.
What about in between our first shell, A to B? Remember that in a conductor, the electric field must be 0. So, when the charge on the inside will be reduced, D must also be B less than R less than C, when the first ordered region. Our inner shell has a total charge of plus 2q, and so that is what will be Q enclosed here. So
going to be
also represents plus 2q. So that means that the electric field can be written as a
FAB,
in terms of
not right down yet, but the book tells us
writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2q, divided by r squared.
Unit vector AB, I'm going to use the x component, negative 2.
And let's see now, C less than R less than D, so now we're in this outer region, okay? So, if we're in this outer region, I know that the electric field must be equal to 0 here in this region. Because when we're in a conductor, the electric field must be 0. That plus 2q here. So I need minus 2q on this inner surface. But in general, you still must be 0 there because we are inside the conductor. And finally, when we are outside of the system, all we have to do is take the total charge of Q plus 2q is minus 2q. So Q enclosed is minus 2q. And we get E to charge inside divided by epsilon times minus 2q over r squared. And let's see now. C less than 1 point. Alright. We can go ahead and graph this. And what do we see? 0, 0 is less than 0. here,
E.
0 there.
Now the denominator
Between B and C,
well, first of all,
we see
FAC according to the book
2.
40 pounds. So it's 40 times.
And now we have to remember the property. So even though this is a quadratic function system, you can get out your graphing calculator and see what happens when we have a negative value outside of your expression that you're working with. So I'm working it now, and I think that all of you should graph it as well.
Plus 40
To see what happens when you have a negative sign outside the
the
expression.
numerator is negative 2 sine 20. So now the denominator is negative 4.7.
Looks like
I'm going to put the 2 plus 2 cosine 20 in the numerator.
now more
27, 6.
when you graph it, there will be two solutions. Make sure that you choose the physical solution.
And
And
now
so in
negative
this instance, it will be outside. Alright, there we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0 if we're working on the inside of this guy, where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell, so 2Q.
23.
Okay, let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so that has to cancel the total charge from this inner shell. So we need negative 2Q in that inner surface.
Add those together to get the result.
Okay? And then what about
done?
the other side? All that you have to do is think about, okay, well there's minus 2Q right here, so remember it has to be out there. Inside minus 2Q.
That didn't go calculate.
So that's the only way for the net but on the charge to the outer surface. It must be the total charge to be minus 2.
23.
Okay, so the large one. Okay, on the inner surface, we need to have total charge. So we need negative 2.
Welcome to EDU World Space.
Okay, so we have two concentric shells,
Answer.
and a radius A, outer radius B of our inner
Yes,
shell,
it is.
and a radius C, outer radius D of their outer shell. The inner shell has
Get alpha, beta, and gamma.
the outer shell has a
Reverse cosine.
minus 2Q, and we're going to find the electric field everywhere. And where the
X,
charge
which is 1.97 over FR.
So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss law.
Change the numerator to 23.
Welcome to EDU World
Gauss
Space.
says that the closed loop integral of E dot dA equals Q, the total charge closed divided by
Negative
epsilon.
46.
Alright, so first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E
And those are correct.
Okay, A less than R less than B. We're in this inner shell, first our smaller shell. This is a conductor. One of the properties is that E equals 0 inside of the conductor. So E equals 0. B less than R less than C. So now we're in this first field. It's also equal. Well, what is the total charge in that region? Q enclosed. Well, it's just the charge of that inner shell. It's 2Q.
Have to determine the magnitude.
So now we can just imagine that it's one charge and say that the electric field
Our given F1 it's along
equals
the negative x-axis.
1
It's a force
divided by
We're also given
4
F2.
pi epsilon times Q, total charge inside, 2Q over R squared. We are at Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Okay, A, well, do our Gaussian surface. Inner shell. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So, E equals 0.
Really any of those forces is break up opposite
That. Now what happens if we are outside of everything? So now what happens if we are doing a Gaussian surface outside of the system? Well, what is the total charge enclosed? So plus 2Q minus 2Q, that equals 0. E equals 0 here as well. We can go ahead and graph this. 0, 0. So we have these regions 0. B to C, right here. Goes something like this, 1 squared. And then it goes straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, of our smaller shell? So, if we are looking at this region right here, well, I know the electric field must equal 0 here. There's no charge on the inside. Here's something reduced. Now what happens if we are outside of it? What about the outer? What happens if we go right here?
Using this information, we can actually find
Well, what is our charge enclosed here? Plus 2Q. That's everything. Electric field due to plus 2Q charge. 0, 0. Plus 2Q. B to C. What about our large inner shell? We go right on this inner diameter. Right here.
our radical trig is so because there's going to be opposite of
Right, now the electric field must be zero here. That means it needs to cancel with this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at this surface. Well, minus 2Q. Then what about this outer surface? It's got to be 0. We have a net charge of 0 here. So, the outer must equal to 0.
Right here, and that's the projection on the XY plane, as well as vertical. So we actually found F2.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of mu dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Maxwell's law, and this is our area element. This is our total charge enclosed in our Maxwell's surface, epsilon 0, just explain. And E is what we're. So let's look for our first region, which is when we have a radius less than A. So for or less than A, well, we don't have any charge there, so that means that Q equals 0, E equals 0. So let's go ahead and so, in order to find a zero field, we're going to write down the Gauss's law of this region. Alright, what about if we are in between A and B, so we're in the shell right here? Well, if it is a conducting shell, then, by definition, it must have 0 electric field. So they're the same thing. And E must equal 0 here. Okay. Now what about this cavity between B and C? So, for B less than R, less than C, less than A, well now we do have some charge. We have the total charge on this shell. That's plus 2Q. 0. So, just in general, we know that the formula for the electric field of the point charge E equals K, which is 1 over 4 pi epsilon, or 99 KQ. Well, divided by R squared. And by definition, we can use this for our region between the C, and we see that the electric field E equals K Q, which is 2 Q. Q right here is the total charge divided by R squared. R squared is just we can write this more explicitly. 1 divided by 4 pi epsilon plus 2Q. So, this one's 2Q just in general. We have the formula over R squared. Okay. Now, what about the region C and D? So now we are in this outer ring. Well, we are in this outer ring. Remember that the electric field must be 0 because it is a conductor. So, for the region between C, less than R, less than D, E equals 0. Okay. Inside that conductor is 2. Okay. And then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we'll just use this formula right here for our regular point charge. And we get our electric field E, C, and D equals 1 divided by 4 pi. Remember that the electric field is epsilon 0 times 6Q. So, for the region over R squared C, G, E, 0. There we go. Those are all of our regions. Now we can go ahead and graph this. And finally, what about right now? So if we manage to graph it, it would look something like this. So we have R, and we have E, and we have when R, A, and D, then we have B, C, 2Q, D, so we'll just use this formula right here. Okay. And we are going to get, and we get region A and B, E, 0, 0. And what about between C and D? 1, 0. originally 0, because we have no charge, times inside that inner shell. And between regions B and C, here's our formula. So it goes as a 1 over r squared. So something like this. Draw the regions. And we see a similar function for when r is equal to d. But this time, we are going to have a different prefactor in front. And it's going to be a little something like that. And so that's that. Now, what about the charges on the inner surfaces? Well, okay, so the inner surface, what is the total charge of the inner surface size of shells? Well, and it has to be 0. Why is that? Because the electric field is 0 on one of them. We have a Gaussian surface right here, so this guy is 0. Gaussian surface, and the charge right there, there's nothing on the inside. And so we see a similar function. So inner, this time we are going to have inner is 0.
Magnitude of the resultant force,
okay, we've got the outer. Now we've got
the total
the outer surface right here. It needs to contain all the charge for this inner shell. Okay, so to keep the inner surface. Okay, and what about for our large? Why is that? Okay, inside you have the inner. So we do a Gaussian surface right here. We know that we must have net 0 electric fields. The only way for that to happen is that there must be an induced negative 2q charge on the inside right here. So this will be negative 2q. Why is that? Because we need E net to equal 0. Okay, this inner shell. Now the outer surface. Our Gaussian surface. Okay. And what about that's just the total charge, 4 plus 2. And that's that. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be, a bit taller than this. Because this is 6 divided by 4 pi, this is 2. The only way for that to happen is that there must be an induced negative 2, which I'll check on the side here. And that's that. Why is that? Because we need E net to equal 0. Okay. The outer surface. That's just the total charge.
Welcome to EDU World Space.
So these are the two components. Both are positive components. That means the force
is that this is, if we were to have units on this,
you can do it directly.
Expect this
3.8 squared
taller.
plus 3.49 squared.
This is 6 divided by 4 pi.
It's coming out to 2.1. So this is a net resultant force, and actually the tan inverse x y over x. Y is 3.49 over 3.8. this gives you a value of 100.6. Counterclockwise.
Welcome to EDU World Space.
Positive x-axis. Because this is the first quadrant. I hope this is clear to me regarding the first quadrant. Whereas the fourth
And this is one of them. It's one problem, but there's two parts. We've got a 5, 12, 13 triangle. 26 kilonewtons. And we've got a 30-degree angle here. And it's 30 kilonewtons. So let's put them into Cartesian vector form. So F1 is negative. And this is one of them. This is one problem, but there's 30. We've got a 5, 12, 30 sine 30 degrees. I is one problem, 22 plus, we've got minus, we've got y direction's also minus, 30, 26 cosine 30 degrees. And we've got j, and it's 30 degrees. The sine, let's put them, angle here, of 30 degrees, is 1/2. So negative, put them, 30 times 1/2 is 15. So I, the cosine of 30 negative square root of 3 over 2, so that would be 15 root 3. So j, F1 is, get F2, negative 30 degrees. It's negative 26 plus minus times 513, which is also minus 30 plus minus 26 times 1213. The sine j, F2 is negative 10 I, just simplifying, plus 24. I, cosine of 30 is 1/2. And checking the work. 30 times 1/2 is 15. And that's correct. Cosine of 30 negative square root of 3 over 2 is negative 26 plus 3.
So here we are given three forces. Let me just write down the forces.
It's negative 26.
That is making an angle of 40 degrees in the vertical. There is this force sort of like this.
F2 is 26.
Force so these are the forces we and the value that is 1 is 15 kilonewtons. He is equal to 36 kilonewtons and F2 is equal to 26 kilonewtons. With that, the angles are given. So this is 38 degrees, and next here we are in the right angle components. This is 5 and this is 12. So here we are based on this, you have to find out the magnitude of the resultant force and its direction. Now this is pretty simple. So what you can do is there is this you can take the total x component of all these forces. So starting with F1. So F1 is sine of 40 degrees, because if you see there the 40 degrees makes an angle from the vertical, right? So the perpendicular component is a sine angle. So the value of plus F3 will also have component to the right. So F3 cos of the angle plus here we will be F3 here, sorry, F2 is in the negative x axis, right angle component. With that minus F2 cos of, let's say alpha angle, based on this, let's find out. Now this is pretty simple. So first of all, let's write f1 value, which is 15 sine 40 degrees plus f3 is 36. Based on this, let's cos of 30 degrees minus f2, the magnitude of the resultant cos is used by so in 45. So now because we can take the vertical x component, so the perpendicular is starting with. So let's see what we have. So f1 is sine of the right, because you can see that the perpendicular cos of the angle of the vertical. So the perpendicular plus it will also perpendicular right. This is 16.8 kilonewton is the total x component. Similarly, Fy will be equal to F1 cos of 40 x, F1 value is vertically upward sine of minus F3 plus F3 sine of 30 cos of this is vertically downward, the negative value F will be sine of 40 plus x sine of alpha cos of 40 same value just plug in F1 is
Welcome to EDU World Space.
cos of 40 degrees minus f3 is 36 for sine of 30 plus 26 sine alpha is 5 over 30. This is 16.2 so again let's see how much cos of 30 this is 3.49 kilonewtons, right? So these are the two components here. So both are positive components. That means the force will be the first quadrant. This will come I can do it directly. 16.8 squared plus 3.49 squared.
Welcome to EDU World Space.
It's coming out to 17.16 kilonewton. So this is the net resultant force, and the angle theta is tan inverse of Fy over Fx. Fy is 2.49. This point over this is 16.8. Tan inverse of this gives you a value of 11.7 degrees. Counterclockwise from positive x-axis. Because this is the first quadrant. I hope this is clear to you. We direct most of the
So far this section seems to be exactly the same as the previous section. Don't know what is different, seriously. So, we're shown that this is 30 degrees. We're also shown that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because in all it's a right angle. What's the magnitude and direction of the resultant force? Well, force resultant in the x direction is going to be 430 plus 800 cosine 45. Force resultant in the y direction is going to be 400 sine 30 minus 800 sine 45. The resultant force is going to be the square root of FRX squared plus FRY squared, and the angle is going to be the inverse tangent of magnitude is direction of y over FR. So let's put all of these into a calculator. It's important that you do the first two, so that you know exactly where that theta is, whether it's downward or upward from horizontally. And so,
Welcome to EDU World
go into a
Space.
calculator, in the y direction is going to be 400 cosine 30 plus 800 cosine 45, 912 Okay, next one. 400 sine 30 minus 800 sine 45. Negative 366 newtons. The square root. The first one and the first two. Where the calculator squared plus the second one 400 squared is 983 and theta is the inverse tangent 912 sine 30 of the second one, or the y direction. Okay, next one. Negative 400 sine 60 over the x direction. First one, negative 22. 21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be 3. Those two are my answers. Let's check in the book. 983, 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction. So again, drawing the diagram and figuring out what it means is most of the battle here. Oops. Y, Z, X, and we need to continue the Z axis downward. We're given F1, which appears to have no X component. Well, that's going to be convenient. So it's a 3, 4, 5 triangle, but it's got no X component. Oops. There we go. Okay. F1. F2 has all three components. Z, X. We need to continue the Z axis downward. But the angles are directly given. X. We need to continue the Z axis downward. X. That's going to be convenient. Know why I'm putting arrows at the end of these. I guess we can book us. And the angle with Y is 120. So yeah, they're all directly given. So let's go ahead and do F1. F1 in the X direction is 0. F1 in the Y direction is, well, it's going in the positive Y direction 3/5 of 450. F2 has angles, well, 45 divided by 5 is 9. 9 times 3 is 27, so that's going to be 270 newtons in the positive direction. F1Z is going to be 4/5 of 450, but is in the negative direction. So that's going to give us negative 361 newtons. So let's move on to F2. This one's actually all pretty straightforward. F2 is, well, it's going in the positive direction. 3/5 is just going to be the 525 times the cosine of positive y direction. X direction is going to be alpha, which is 45. 27, so that's going to be 2y is 525. The cosine of the y direction, right? 27, so that's 120 degrees. And F2z is just going to be 525. That's going to be pretty straight cosine of z, which is 60 degrees. So this y one should end up giving us a negative number. The other one should be positive. So let's put them into a calculator. X direction is just going to be 525 and the sine of 45 gives me 371.2. 525 cosine 120 negative 262.5 newtons, and 525 cosine 60 is just going to give us 262.5. Okay, so now we have to add them together. Adding the x components, well, there is only one x component. So that's going to be, so I'm going to write it in vector form. 371.2i f. So now I'm going to do 270 minus 262.5. I don't trust myself, so I'm just going to do 270 minus 262.5, 7.5. Plus 7.5j, and then in the k direction we've got negative 360 plus 262.5. So that's going to be, so now we have to add adding the exponent will give us negative 97.5. So I'm going to write it in vector form. So now I'm going to do 270 minus 262.5. Okay, right. We need to sketch the vector and find the magnitude and the height. Well, sketching the vector is what I would do next. We've got 371 in the I direction. Then we've got 7.5, which is almost nothing in the j direction. And then we've got a negative k direction. So it's going to be like down over there. Maybe something like this. Alright. So now, F sub r square root 371.2 squared 7.5 squared plus negative 97.5 squared. And a calculator? It's going to be 384. Alpha. 371.2 over 384. Beta and gamma are going to be very much the same.
Welcome to EDU World Space.
So let's solve this question by this question here.
Alright, inverse cosine. Oh, 371.2 over. That's the bottom. 14.8. Just put 7.5 in the numerator. That's the same. 9 and negative 97.5. That's the same. 100. Now I'll check.
E comes out
Welcome to EDU World Space.
So in this question, radius is right, material values potential having a radius over here. So here, right, and we are going to determine the direction right? Now, thing to note over here is that as there is no load that is applied over here, right? So it means that if there is no load, so there will be torsion present. And as there is only torsion present, it means that it would be no stresses. It means the stress in the x direction is equal to stress in the y direction, that would be 0, right? And if there is no stress, it means that there is no normal strain, right? So it means that the strain in the x direction and the strain in the y direction is 0, right? So now this is also let's write the strain over z equation for 45 degrees, right? Strain over z equation for 45 degrees. Now cos it will get 1.5 degrees. So that is 5.
I like to write
Right? Now what we need to do is that right on the cos that you bring it down, right?
is F2
Sorry, 135. Right? So again, these two terms will become frequency for the delta and solve it and get that is equal to negative gamma by 2. Let's do it. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to V times V divided by 2, right, and we call that torsion is equal to now V times. Now what we're going to do is that we're going to compare these two equations and we'll solve it for gamma, right, and we'll solve it for gamma means expression, right? So what you're going to do over here is that you're going to plug in the values and you'll get that gamma is equal to right? Right? So what is that in equation 1? We'll get that it is equal to
they are both positive.
positive.
So
That is equal to positive 5 and this is equal to negative 0.05, right? So
Welcome to EDU World Space.
So in this question we are given
is also in the positive direction.
right, and
Surprised that everything is in the positive direction.
What you're going to do is
So, I need to write this in Cartesian vector form.
right, theory is going to be of help over here, right? And we're going to take help of the example 10.6, right? So we can start working on the problem. Now to be able to build a pyramid, we need the answers, right? So the answer we are going to use right? So after that, it's really after the problem is right? And that is equal to sum of the three divided by 2, right? And plug in the values and we get that it's equal to 629. Right, and now we also use the radius of the pyramid, right? And that can be found out that under root difference of the space when it's going to right here and plus square space right, so again you have all the values and just plug them in and get that equal to 4 right, and that is equal to
Now, is this diagram
Now all you need to do is that you need to draw circles.
Okay. So, continue this through. We've got a point down here, which looks like an easy one.
And this is right? So
Here.
this is the number circle, right? That was right. Now what I need to do is that principal space for here is right? So we're going to take the head part of the circle, right? Principal drawing circle, now we need to find out the other principal space, so that is the block, right? So 600 plus 346 is 24, and right now that is equal to 946.
This, I'm going to indicate that this is...
Right, now what we need to do is that we find out the maximum
and this is 200.
Right? So for that we have the expression that
Alright,
gamma
so the distance
of
from A to
maximum
B
in the right divided by 2 right?
going
So
to be
this is simply
X direction is
now we
going
shift
one
to the
and a half.
other right, and we have a line
Y
gamma
is going to be negative
R
degrees to the middle of 1 foot. This, so the Z direction is going down 4 foot.
I think that I know the difference of the principal space and that height. So we calculated and we get that distance right, and that is approximately equal to 6 times. Right, now since the vector space they have the same sign, right, then the absolute vector space would be
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field. So to begin, we need to write down Gauss's law. Closed line integral of the closed loop integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals kq, total charge inside, divided by r squared. This is like k is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, which is equal to 1 divided by 4 pi epsilon naught.
FAB.
Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then Q is 0, so the electric field must also be equal
Welcome to
to
EDU
0.
World Space.
vector
Hmm.
use the
What about in between our first shell, A to B? Well, remember that in a conductor, the electric field must be 0. So, if there's no charge on one side, then reduced E must also be 0. B less than R less than C, minus first order region. Our inner shell has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed is plus 2Q. So that means that the electric field can be written as a point charge case of epsilon or just as K. So writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by R squared. And let's see now. C less than R less than D, so now we're in this outer region. Okay. So if we're in this outer region, I know that the electric field must be equal to 0, as when we're less than the conductor, the electric field must be 0. Inner shell is plus 2Q here, so we need minus 2Q on this inner surface. And so that, but in general, E still must
40
be
times
0 there, because we are inside the conductor.
on the
And
denominator.
finally, when we are outside of the system, so that means that the electron we have to do is take the total charge minus 4Q plus 2Q is minus 2Q, so Q enclosed is minus 2Q, and we get E equals 1 divided by 4 pi epsilon
2 plus 2
times minus 2Q times the total charge inside, which is 2Q, divided by R squared. Alright,
plus 4 squared.
so we can go ahead and graph this. And we can see 0, 0, less than that.
The numerator
0 here,
negative G times
0 there, in this outer region between B and C. We see
7.
2.
I'm going to put the 2 plus
4 pi epsilon 0 on here. So that's minus 2Q on this inner surface. And now, I have to remember one of the properties, so still, even though this is a quadratic function, because you can get out your graph
and now negative.
and see what happens when you have a negative value outside of
Add those together and get the result.
And so I'm graphing it now, and I think that all of you should
6.84 minus
see what happens when you have a negative sign outside of the expression.
27.6 minus.
It looks like these something like this.
And now negative.
More, excuse me. When you graph it, there will be 2 solutions. Make sure that you choose the physical solution. And so, in this instance, it will be simply like this.
And we're still not done.
Alright, here we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0 if there's nothing on the very inside of this guy, whatever the dot is. So, this guy must be 0 outside. What about on the outer surface? Outer surface must be the total charge on the shell. It's 2Q. Okay, let's look at a large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge from this inner shell. So we need to see the negative 2Q on that inner surface. And let's see now. Okay. And then what about on the outer surface? Well, on the outer surface, what you have to do
That's the correct answer.
is, think about.
Yes, it
okay,
is.
Well, there's minus 2q right here.
And then to get alpha, beta,
Well, it has to be out there.
there's cosine
Minus 2q.
FR X, which is
That's the only way for the
1.17
net
over FR,
charge
which
to
is
let you
2.1. Not in
when you
calculus.
graph it, there will be minus solution to choose the physical solution. And so in this instance, it would be simple.
Still not done. 7.83.
Okay, so now we can get
Beta. Just have to change the numerator to 23.
Welcome to EDU World Space.
these shells.
Yes, it is.
Okay, so we have two concentric shells in a radius A, outer radius B of our inner shell, and a radius C, outer radius D of our outer shell. The inner shell has a total charge of plus 2q, the outer shell has a total charge of minus 2q, and we're going to find the electric field everywhere, and where the charges are located on the outer surface. Let's get started. Outer surface. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9
This seems like a
times
fairly
10 to the 9.
complicated one.
It's also equal
As always,
to 1 over 4 pi epsilon.
diagram.
Epsilon is just a constant.
We've got F2.
So we need negative. Also remember Gauss' law. Here it is.
200 newtons. We've got
It says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon.
260.
Alright, so, first region, radius
And
less
it's in
than
a 5, 12, 13.
Okay? We are right here in this little green dot. We have
And
no charge there.
we've got
With no charge,
F1.
Q is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell, first, our smaller shell. This is a conductor. One of the properties is that E equals 0
Get
inside
alpha beta in the direction
So,
of
it's to be 0. B less than R less than C, so now we're in this first ordered region. Well, what is the total charge in that region? Let's see when closed. Well, just the charge of that inner shell, plus 2q.
First of
So,
all,
now we can just imagine that it's a point charge. We can say that the electric field, E, equals 1 divided by 4 pi epsilon
the resultant
times Q, total
x
charge inside,
direction will be the x component of
2q
all of them.
over
So it's
R
going to
squared.
be
There it is.
F1 sine 5.
Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our best to surface for somewhere
F3, which
here.
is 260.
What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor.
X direction is going to be 5.
So, E equals 0. There it is.
Let me simplify that.
Now what happens if we are outside of everything? So now what happens if we are given a Gaussian surface outside of
260 divided by
Well,
13
what is the total charge enclosed?
is 20.
Plus 2q minus 2q, that equals 0.
200 is 300.
E must be 0 here as well. We can go ahead and graph this.
Force
0,
result
0. So we have these regions of 0. The electric field is B to C, right here. K does something like this. It's 1 over R squared. 9.
minus
And then it goes straight back to 0.
260
10 to the 9.
times 12.
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, of our smaller shell? So, if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside here, so we can reduce times to A equals Q, the total charge closed divided by epsilon. What about the outer? Alright, so, first right here, radius less than 1. What is our charge? We are enclosed here, dot.
And the result
Plus
got
2q.
F1
Everything is in 0. We have an electric field due to a plus 2 in the
square
charge.
root.
There it is. this inner shell,
F1
shell, is 2Q.
by
What about our large shell? We go right on this inner diameter, right here. B less than all resistance C.
where
Okay? We know that the electric field must have 0 here. That means it needs to cancel with this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at the surface. Minus 2Q. 1. Then what about this outer surface? It's got to be 0. We have a net charge of 0 here.
and we want that result force to be 450 newtons.
So the outer shell, C less than all of 2.
Now also
Must equal 0.
we want the inverse tangent, which is 260.
What is the total charge in here?
F1 times sine phi minus 240 over F1 sine of phi plus 100
Now what happens if we were outside of it?
to be
So now what happens if we
30
are
degrees.
in Gaussian surface?
260 divided by
Welcome to EDU World Space.
Plus 2Q minus 2Q. Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B. The outer shell is bound by the radii C and B. We're looking for the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says, that the closed line integral of v dot dA equals the total charge that is enclosed in our region divided by epsilon squared. So in general, this is our Gauss's law, and this is our area element. This is our total charge enclosed in our Gaussian surface. This is epsilon 0, just a constant, and E is what we're looking for. So let's look for our first region, which is when we have a radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0.
Now let's think about what it means to cancel. Between 0 and 9.
Alright, what about if we are in between A and B, so we're in the shell right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field. So we have the same thing. E must equal 0.
0 to 90.
Now what about this
And I'm
cavity
going to scale my
between B and C?
y-axis from 0
So,
to like
for
5.
B less than R less than C, well now we do have some charges. We have a total charge on this shell, plus 2Q. So, just in general, we know that the formula for the electric field of a point charge, E equals
I see a point of intersection.
K, which is 1 over 4 for epsilon, or 99, K cubed,
But I'm going to zoom in so I can see enough.
divided by R squared. We can use this for our region between B and C, and we see that the electric field E equals K, see if we can find Q to Q right here is the total charge divided by R squared. R squared is just so. In order to find the electric field, we're going to write down Gauss's law. We can write this more explicitly, which says 1 divided by 4 pi epsilon, where the line integral of v equal times 2q over Okay, now what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must be 0 because it is a conductor. So, for the region between C and D, E equals 0. We don't have any charge there, so that means that inside that conductor. 0?
This
Okay.
is the
And then
force.
finally, what about if we are outside of this object?
XY component of the force is 7 kilonewtons.
Well, when R is greater than D, then the total charge equals, which is 4q plus 2q, 6q. So we just can use this formula right here for our regular
Cosine.
charge, and we get our electric field E
Adjacent over
equals
so F
1 divided by
7
5
over cosine 30.
epsilon 0
So let me get that.
times 6q
Calculator here. 7 over cosine 30
r squared.
is 8.08 XY component. Now, need to get the
These are all of our regions. Now we can go ahead and graph the
direction
just in general. So if we wanted to graph it, it would be like this. So we have
the first thing that I noticed is looking from above.
and we have
Looks like this. X,
C,
Y,
D,
kilonewtons.
okay,
40 degrees.
and
Looks like
we are going to
from
get
above.
between regions A
And we
and
can
B.
envision a triangle here.
And what about
And
region
so,
D? Okay. Originally, 0, because we have no charge. Inside of that inner square. And between regions C and C, here's our time direction. So, it goes as one over r squared,
First thing I noticed,
something like this.
and the force in the Y direction is
And we see a similar function for when r
the
is
force in the
D.
Z direction.
However, this time, we are going to have a different prefactor zone, and it's going to be this outer ring that
30
equals and so that that's that. Now, what about the chart of the inner surface area?
30.
Well,
It's also
okay, so the inner surface, we find what about the inner surface is has to be 0. Why is that? Because
not quite that
the electric
simple.
field is 0,
Y,
D, we have a Gaussian circle,
minus beta. I can do that as N.
surface, and charge out there, there's no charge on the inside,
So,
inner,
from the first equation, we get alpha equals
inner is 0. 1
the inverse cosine of 7
Okay, what
over
about the all the outer surface right here
beta equals inverse cosine.
needs to contain all the charge
F
for this inner shell. That's 2q.
and gamma
Okay. And what about for our large?
of 7 over F tangent. From the first, we can put all of these in the calculator, understanding that F is 8.08.
Here's the inner. So we do a Gaussian surface right here.
Sine
We know that we must have net 0 electric field. The only way for that to happen is that there must be an reduced negative 2q charge on the inside of the plane. So it must be negative 4 degrees.
Now we'll put in the
Rise up
sign.
because we need net 0. Okay? On the outer surface,
Sine 40, that gives me
that's a similar function.
6.2 degrees.
That's just the total
And
charge.
7 over half tan variable.
And that's that.
Now, this one is not.
Also, another thing to remember about this graph
If you look at
is that this is
the angles,
we
really
which have units on this. We expect this to be
and I'm going to try to draw
taller
here.
than this. Because this is 6 divided by 4 pi. This is
Y.
2.
I'll put in the sign. And
This is the way to check. And that's
okay,
that.
the angle for beta is in this angle, not this angle. And so we really figured out 180 minus.
Welcome to EDU World Space.
And so, beta really is 180 minus 123.8. Let me check the answers here. This is 2. I like these two-part problems, and this is one of them. It's one problem, but there's 2 parts. We've got a 5, 12, 13 triangle, 26 cones, and we've got a 30-degree angle here, and it's 30. So let's put them into Cartesian vector form. So F1 is negative. This is one of them. One problem. There's 30. Got a 5 sine 30 degrees. I.
This is
Plus, nope, minus, got y direction there also minus 30 cosine 30 degrees. J. The sine, let's put them of 30 degrees is 1/2. So negative 30 times 1/2 is 15. So I1, the cosine of 30 degrees is square root of 3 over 2. So that would be 15 root 3 J. F2.
Welcome to EDU World Space.
It's negative 26 plus minus times 513, also minus 30 plus 26 times 1213 is sine J. F2 is negative 10 I, just simplifying, plus 24 checking the work. And that's correct. F2. I like these two parts. It's negative 26. That's one problem. I'm going to treat this as a continuation of number 56. And how I'm going to do that is I'm going to first of all retain most of my work, but I'm going to delete basically all this green stuff here at the bottom. F2 is negative 5, simplifying, and it's 30. Okay, got that. Now, put them. We want the resultant to be a minimum, and we want 5 to be 30 degrees. So I'm just going to put it in there. I'm going to do that and look for where F1 is a minimum. Most of my work, but I'm going to a graphing calculator. I wish I could show it to you, but it slows down my computer way too much. So I'm going to write y equals the square root. Okay, got that. F1. Well, F1 is going to be F. We want cosine the result of third minimum minus 240 squared plus F1, which is X, sine of 30 plus 300 squared. And look for where it's negative. That gives me a graph. I'm going to zoom out here until I can see it. I wish I could show it to you. I was zoomed way in. Oh, I want this to be a minimum. The minimum is at F1 equals 57.8 minus 240 squared plus F1, which is X, and the resultant is going to be the Y value on my graph, 380. That gives me a graph. I'm going to zoom out here. We're going to treat this as a continuation of digits for 76. Get 380. I want this to be exactly what it's retain most of my work, but I'm going to use that. Basically, alright, we're doing the same problem again. I retained the drawing and the general information, but now we're just told a different value for alpha. We want alpha 3, the resultant to be a minimum, is going to be the Y beta 3, 300, and gamma 3.
Welcome to EDU World Space.
So I'm just going to put it in there. F3x is just going to be F3, which is the 800.
So, to begin, we need to write down Gauss's law.
Cosine 120.
Cosine integral equals loop integral VA equals total charges divided by F1. Also remember that we can say that the electric field equals KQ, total charges divided by R squared. K is just a constant when it goes into the 9. You can also write it in terms of epsilon, and the divided by 4.
Okay. So now we just have to add them all together.
Alright, so right at this point, on the inside of this inner shell, there is no charge here. The electric field is just going to be F3, which is the 800. F1x is 350 root 3. What about returning our first shell, A to B? Remember that F in
FRY is 800
So, there's no charge on the inside, nothing's reduced. E must also be 0.
plus the Y
B
direction.
less than or less than C, so
350.
this first ordered region.
That's
Our inner
40.
shell has a total charge of plus 2Q. And so that is what would be Q enclosed here. So Q enclosed is plus 2Q. So that means that the electric field can be written as a point charge in terms
Z direction.
of writing it like that. We get
360.
1 divided by 4 pi
X is 350.
epsilon 0 times the total charge inside, which is 2Q, divided by r squared. And let's see now. C less than or less
Put this into calculator.
So, from this outer region, I know that the electric field must be equal to 0 in this region. Because it means that
800 cosine 120
at plus 2Q here.
plus
So we need
350
minus 2Q on this inner surface.
3
But
squared
and still
plus 800 cosine 45
And finally, on the outside of the system,
plus
we
480
will take the total charge on this
squared
minus 2Q
plus parentheses 800 cosine 60
and
which
we
is
get
400 by the way
divided by
plus 360
times minus 2Q
1603 newtons. I mean pounds.
We can go ahead and graph this. And let me see. 0, 0.
And let's check if that's correct.
0 here.
3. Yep.
0 there. Times
Alpha is going to be cosine of FRX over F.
now,
Just putting that into a calculator.
even though that this is a quadratic,
For X.
you can get out your graph and see what happens when you have a negative value. So, outside,
82.6 degrees. Then beta.
so I'm
Putting in the numerator 800 cosine 45 plus 350 plus 480.
so that to see what happens when you have a negative sign outside of the expression.
Going to be gamma. Is
It looks like
2 So checking the answer.
divided by more, excuse me. When you graph it, there will be two solutions. Make sure that you choose the physical solution. And so, in this instance, it would be simple. So, alright, here we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0 inside of this guy, so that green dot is. So, we're describing the outer surface must be the total charge of the shell. Okay, let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge on this inner shell. So we need a negative 2Q on that inner surface. Go ahead and grab this. Okay, and then what about the outer surface? On the outer surface, all that you have to do is think about, okay, well there's minus 2Q right here,
X.
What has to be out there? Minus 2q. That's the only way for the net charge to be like this. Outside
82.6 degrees. Beta.
Then we can multiply the numerator 8 by
45 plus 350 plus 480.
see what happens.
Welcome to EDU World Space.
Okay, so we have two concentric spherical shells, and a radius A, the radius B of our inner shell, and a radius C, our radius D of our outer shell. The inner shell has a total charge of plus 2 Q, the outer shell has a total charge of minus 2 Q, and we're going to find the electric field secondary, and where the charge is. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is. So Gauss says that the closed loop integral of E dot dA equals Q, the total charge enclosed, divided by epsilon. Alright, so first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell, or first, our smaller shell. This is a conductor. One of the properties is that E equals 0 inside of a conductor. So, E equals 0. B less than R less than C. So now we're in this first order region. Well, what is the total charge in that region? Q enclosed? Well, just the charge of that inner shell, that was 2Q. So, now we can just imagine that it was a point charge and say that the electric field E equals 1 divided by 4 pi epsilon times Q, total charge inside, 2Q over R squared. Here it is. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface for somewhere in here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So, E equals 0. There it is. That isn't too bad. Now what happens if we are outside of that?
Welcome to homework.
So now what happens if we are doing a Gaussian surface outside of this? Well, what is the total charge enclosed? Plus 2Q minus 2Q. That equals 0. E must equal 0 here as well. We can go ahead and graph this. 0, 0. So we have these regions 0. B to C, right here. So it goes something like this. It's 1 over R squared, point charge, and then it goes straight back to 0. Alright, now let's look at where these charges might be located. So what is the charge on the inner surface of our smaller sphere, of our smaller shell? So if we are looking at this region right here, it's also equal. Well, 1, the electric field must equal 0 here. There's no charge on the inside. There's nothing reduced. It must equal 0. Also, what about the outer? Go right here. Well, what is our charge enclosed here? Plus 2Q. So the integral of E dot dA Q, the total charge enclosed by the electric field due to the plus 2. Alright, so charge region, radius less than A. Okay? plus 2q. Right here, this little green dot. What about our large shell? No charge. We go right on this inner diameter, so right here. Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land at this surface.
So I guess I'm wondering, why did they tell us that
And what about this outer surface?
2000 hertz
It's got to be 0. We have a net charge of 0 here.
resonant
So now we
frequency?
can just imagine
I guess they do that because
1. So the outer
omega 0
4 pi epsilon must equal times
1
q
over the square root of L times C.
squared.
And so,
Alright, now we're in our outer shell. C less than
1,000,
C less than D.
or rather 2 times pi times 2,000, not the omega 0,
In here,
is going to be
what is that? We're inside the
square root
Welcome to
of
EDU
1
World
over
Space.
LC. Also,
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound with the radii A and B. The outer shell is bound to the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere.
is 1,004.
C.
Okay, good.
So, in order to find the electric field, we're going to write down Gauss's law,
Over omega 2
which says about the closed line integral of u dot dA, where these charges must be equal
is
to the charge of the enclosed in outer region divided by epsilon 0. So, in general, this is our Gauss's law, and this is our area element. This is our charge enclosed in our Gaussian surface. This is epsilon 0, just a constant. And E is what we're going to. So let's look for our first region, which is when we have a radius less than A. So for or less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0.
divided by 2 and pi and the 2,000
E equals 0. This region. Alright, what about if we are in between A and B, so we're in this shell right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field.
now.
So we have the same thing. E must equal 0 here. Now what about this cavity between B and C? So, for B less than R, less than C, well now we do have some charge, and we have the total charge on this shell, plus 2q. So, just in general, we know that the formula for the electric field of a point charge, E equals K, which is 1 over 4 pi epsilon, or 99, KQ,
49 now.
divided by R squared.
Make sure I got that right. 1 over
We can use this for our region between B and C, and we see that the electric field E
is
equals
1 over omega C
K
over 2 pi FC.
Q, which is 2 Q right here is the total charge divided by R squared. R squared is just 4, write this more explicitly,
That looks good.
1 divided by 4 pi epsilon.
Equals
Is 2Q over R squared. So, in order to find the electric field, we're going to write down this. Now, what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor of. So, for the region between C less than 1 D, E equals 0. Inside that conductor. So let's go. Okay. And then finally, what about if we are outside of this object? So what happens if R is greater than D? Or less than A? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just use this formula right here for our
R squared
charge, and we get electric field E, right? What about if we are in between equals 1 divided by 4 pi
XL
so epsilon 0
minus
times 6Q
impedance is the
over R
squared.
squared. 1 divided by 4
R squared. Okay. Now, I should be careful with my digits.
Those are all of our regions. Now we can go ahead and graph this.
There's a way on here to
So if we wanted to graph it, it would look something like this. We have R, and we have E.
We were given
And we have A,
three significant downs to begin with.
C,
We had 4 for 1
D.
Let's look at the problem again.
Regions. Now we can go ahead and graph this.
XL and XC have 4 significant digits.
And we are going to get
Frequency is questionable. Given. There it is.
And what
So,
about
let's keep going.
Zero.
Where was I? Okay, so I wanted this. I'd like this to be 3
Originally,
significant digits, but it's
0
not a good way to
inside of that
do that.
inner
Now,
shell.
since I used the F4 button,
And between regions
anything
B
up
and
here,
C,
I'm going to highlight in yellow.
so it goes into
The
1
F4
over R
button, so
squared.
it stays. It's going to continue to refer
Something like this.
to the same.
Originally.
And
And
whereas all the rest
we
of
see a similar function for when R is down. And this time, we are going to have a different vector in front, and it's going to be a little steeper.
And this one I need a little less.
And so that is similar function. Now, what about the charge on this surface?
And there we have it. By the way, just to check my work,
Well,
if I put 3,000 in, I should get 1884.
okay, so the inner surface, what is the total charge on the inner surface?
This is a good line
What about the charge
to check your work.
0? Why is that? Because the electric
now,
field is 0 and when we have a Gaussian surface right so this
want the
guy.
same set of paths to
So, have the charge right there, we have the inside,
So, back to my spreadsheet. All of these is a
Inner.
function of x. Well, that should be easy. I want it to be a scatter plot because these values here are not equal to space. Check. So I'm going to insert a chart now.
there we go. The outer.
That's not a scatter plot. So
All the outer surface right here needs to contain all the charge for this inner shell.
it looks very much the same when you here are not actually space. The numbers are going to. I want it to be a scatter plot. These values charts are just like space. So I'm going to insert a chart now. Used to Microsoft Excel. Boy, that looks close to the same. I'm going to do a scatter plot just to be sure.
The inner.
Customize it.
Just to continue, so we do a Gaussian surface right here for this inner shell. We know that we must have net 0 electric field.
Chart style.
The only way for that to happen is that there must be an induced negative 2q charge on the inside of here. So it has to be negative 2q.
For a series.
Why is that? Because we need E net to equal 0. Okay? On the outer surface, so for a Gaussian surface, we know that that's just the total charge, 4 plus 2. And that's
Let's just go down here.
Also, another thing to note about this graph
Let's go back to
is that this
the
is,
line chart.
if we were to have the units on this, we would expect that this would be
Is there a difference?
taller than this. This is 6 divided by 4, 5, this is 2 divided by 4. That's just the total charge.
10.
Of check.
Just go down here.
And that's that.
Let's go back to just go down here. It almost looks like a straight
Also,
line.
another thing to note about this graph
Let's go back to
is that this is
line.
units.
I think this will work. So apparently, when Google puts in a line chart, the line chart is not just a
Welcome to EDU World Space.
line graph. The line graph wouldn't be able to tell the input numbers. So this is good. So now I have it. Interesting. It almost looks like a straight line. I think this will work. Now what am I supposed to do? As a function of the natural logarithm. So of x. I didn't see that. So line graph must be what I'm gonna do then. So this is. I'm going to move this over. This is good. Like this. I'm going to copy this. As a function of the natural logarithm. Now I'm going to put natural logarithm. As a function of the natural logarithm. So ln. Drag it down. I'm going to do this. And now. Okay, that is. Wow, I know that changed everything over here. So that did. Whoops. Okay, so how am I going to do this? It used to refer to B6, but now I need to make it refer to A6. So I'm just going to do this. I could probably change my chart to be a logarithm chart. I know, that's not going to do this here. So that, whoops. I know, that changed everything. E3. Whoops. Used to refer. Okay, so how am I going to now? No, I'm going to used to refer to B6. Now I need to make okay. Now I should be good. So this shouldn't change this. And now I can just. That shouldn't change that. Nope. There we go. Okay. So now our x-axis is the natural log. Now I should go. This shouldn't change. Okay, great. Now I should go. And now this shouldn't change. And now I can go. Okay, that did change it somewhat. I'm wondering if I set my axis from what's that middle? That middle is 7.3. I bet it's going to be symmetrical. If I set my center point to be 7.3. Let's go ahead and do that. I'm going to set my x-axis. Nope. I'm looking at horizontal axis to go from one curve to the I'll just go from 6.3 to 8. If I set my, I bet it's going to be symmetric. We're not going to see everything, but I just want to show you my symmetric. Wait a minute, that doesn't look right. 7.6. Okay. Axis. Horizontal. Let's do 6.6 to 8.6. Now that should be interesting. And so you can see that this yellow line of impedance is symmetric, and the 7.4 capacitive resistance and the inductive resistance are mirror images of each other. That's pretty cool. Now 6.8, and so you can see this yellow line
We use trigonometric relation to the yellow line with amplitude. So y is equal to y1 plus y2 and by substituting value y is equal to 70 degrees right, and this can be written as 12 into 2 plus 70 degrees divided by 2 into cosine of minus 75 divided by 60, which is equal to 25 times cosine of 35 plus times 9 into 4.5 times c 35 degrees divided by, and therefore amplitude is amplitude is equal to 24, which is equal to 25 degrees, which is equal to 19.79 centimeters, and phi is equal to 35 degrees. Right. And further, let's do quality. So in the method of phasors,
Welcome to EDU World Space.
and we define the x-axis and y-axis and so on to then y-axis and y1 and y-axis
Well, we have using and using obstacle. To find obstacle, we have to determine the center and the area of the circle. Center can be found in some basic equation, and it is at 6
Welcome to EDU World Space.
0. So it's at the areas, we found this includes equation, and it draw a circle. This point will be option 1, this point will be option 2, and that is this point to the maximum increment just there. Number 2. So, for the actual one is just the average scale as the values, which equal to 35 degrees. This is option 2 is just the here, 5, 10, and this is the maximum increment system is also 15 centimeters. Now for the maximum absolute achievement, I have to draw another circle which touch the origins and the action 2. Then draw the big circle that cover those two circles. This point, the one exit value of this point will be the absolute maximum she's going for 2. So, it's just that absolute maximum she's going is equal to maximum minus 13.5 sine 80 degrees plus 75 sine 17 times
Welcome to EDU World Space.
Minus to find the equivalent at the orientation of 30 degrees according to the original thing. So first we have to draw the more circles, and to draw the more circle,
Welcome to EDU World Space.
And the radius of the circle, which we already combined. And then we have to determine the outward plane of the circle, which is by maximum x and x minus 9 I will call this one A.
Welcome to home.
Yes, I will already know.
Because we're supposed to use technology for this, I'm going to use Desmos.com. And my equation for power is 1 half times delta V max squared. Delta V max squared,
60 degrees,
which is 1. Oh wait, no, we're given RMS. So because we're supposed to use technology, I just want to use the RMS squared. Because we're supposed to use 1 squared. And over z squared. Z is the square root of r squared. R is 1. Oh wait, no, we're given RMS. So plus 2. No, we're given RMS. I. So just 1 squared. F. But F representing X. 2 pi F is 1 squared times L. L is 0.001 over 1 milliampere. Minus 1 over 2 pi F. this is 1 nanobit, so that's going to be 1 times 10 to the negative 9. There. 1 over omega c. Square that also. Alright, we're supposed to make a... Oh wait, I'm not sure yet. So that would be Vmax squared over z squared, and I have to multiply by r. R is also 1, so I guess I am. Okay, so I'm making a graph of that. 1 over zoom out here. Square that all there.
All the time.
1 over we're supposed to make square that also. I'm going to change my axis. My y-axis, I'm just going to go from 0 to graph of that. Okay, so I'm making a graph of that. Okay. Why don't I see anything? Aha! There we go. Y-axis. So it does go from 0 to 1. Y-axis power goes from 0 to 1. 0 almost all the time, but we have a peak 0 at 159,000 hertz. Aha! And I want to verify that the width of the resonance peak or half the maximum. So if I want to do that, half the maximum, when the maximum is 1, well then all I have to do is subtract half of that off. 9,000 hertz, okay? And I can look for the x-intercept right here.
Welcome to EDU World Space.
So in this question we have been given the date of the reactions right? So in this
And
acting on the y direction is equal to 550 and then we can use it as right? And the
it's 275.
negative 650 into
So I'm supposed to verify
right,
width is r over 2 pi l. So let's just do that. R is 1
and we are going to use
over 2 pi and l
circle
0, 0, 1.
right, and what is that we are going to fill the circle and so that we will get x and
What it said is r is 2 pi l.
right, so we have
R
all the
over 2 pi l is
if red value of the space,
width
right,
pi
so we are going to use some of the space divided by 2, right, and we calculate it to get us equal to 425 right. Right now, all we need to do is that we need to find out the radius of the circle, and we have the expressions of the circle for radius as well, right? So we have underneath the
squared in the circle
and
get rid of the square root. I just put z in it. That's going to be z squared. Now let's not take out this 0.5. Back, we'll see it's still up to 1. The max is still 1. Now I'm going to subtract half off. Alright, I do see it. Now, let's zoom in and see what we got. It's 159,235.
Right, now what we need to do is that
minus
the circle. Right, so let's take a look at that.
Yay! And look at that. Now
So I
I've
can
got
see over here that this is the
160.
at with the state of strain is occurring, right? So we need to measure the angle from this point, right? Now the principal strains are easy to find, right? Because we take the help of the circle. Now for that, principal strain is equal to 4c negative r, right? So we have the values which was negative 10 that will be 57.8 plus 10 to 6, right? And the other principal strain is 4c plus r, right? Again, you have the values, just plug them in and find out. So value, you answer in your numbers, and then you answer to now the principal strains are negative 10 to r negative 6. Right, now that we have the value of the principal strain, we need to find out the maximum, right, in plane shear strain, right? That is given by this divided by that's equal to r, right? So when we shift this to over here, we can easily find out the value of the maximum in plane shear strain, right? So gamma equals maximum in plane, that is equal to r, that is equal to the difference of the principal strains, right? So you have values, right? That is, you just need to plug them in, and you have your value, that is 6 minus 6 equals 10 raised to the power 6. Right, now since the principal strains, they have the same sign, right? They have the same sign. The same sign means that we can directly have the expression for the maximum value of the strain, the shear strain, right? That is maximum principal strain is equal to 6. This includes our solution. Right, now since the principal strains, they have the same sign, right? They have the same sign.
Welcome to EDU World Space.
So let's solve this question. So in this question we have epsilon A equals to epsilon x square theta plus epsilon y into minus square theta plus gamma xy cos theta sin theta. Following this, epsilon x equals to epsilon y equals to 0. Substituting the value, we get gamma xy equals to be 5.7 that is to 1 minus 4 to a is to y1 is mentioned by r a1 minus y2 r sin x. Doing this, we get 2as 0.065 MB. Now we have plus tau gamma xy as plus b u a by I is x by I is tau x is e u a by I by y plus 5.74 d4 minus d4 d minus d. So that means tau xy s plus is equal to e as. Now we have tau xy plus to g as gamma xy. So this is what 38.97 into e plus to 5.6 into 10 raised to power 6 5.7 into 10 raised to power minus 4. Phi comes out to be 0.05. Tau xy s
Welcome to EDU World Space.
So in this question, the radius is equal to right? Material that is used over here is d. The tension that is applied over here is of magnitude 2 kN/meter, right? And we are required to determine the strain along the x dash direction and the y dash direction, right? Now, the thing to note over here is that as there is no load that is applied over here, right? So it means that if there is no load, so there would be only torsion present. And as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction, and that is equal to 0, right? And if there is no stress, so it means that there is no normal strain, right? So now it means that the strain in the x direction is equal to the strain in the y direction, so that is equal to 0, right? So now since this is on pair up, so let's write the strain as equation for 45 degree, right? Strain was an equation for 45 degree is right, and if there is no strain along the x direction, right? So strain along the x direction cos square 45 strain along the y direction, right? Sorry. This is on strain along the strain along the y direction is 45 plus gammas of xy times 45 times cos 45, right? Now we just discussed that the strain along the x and y direction right is 0, so it means that the system terms will become 0, right? With this term, so solve it and you will get that it is equal to positive sigmas of x, sorry, gammas of xy divided by 2, right? So let's say that this is equal to 1. Now what we need to do is that we need to write the strain as an equation for 135 degree. Now how did we get 135 degree? So 45 right? So now what we need to do is that we need to write the reset equation for 45 degree. So sorry, have 135 degree. 135, 135, we got right cos 135 degree, and now we get sine 135 right? So again, these two terms will become 0 and we only left with this term, and solve it and we get that it is equal to negative gamma by 2, right? Let's see what this equation will be. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to d times e divided by j, right? And we call that torsion is equal to g times gamma. Now what we are going to do is that we are going to compare these two equations and we will solve it for gamma, right? And when we solve it for gamma, we will get this expression, right? So what we're going to do over here is that we're going to just plug in the values and we will get that gamma is equal to torsion formula 6, right? Which is 0.50 torsion, right? So just plug it back in equation number 1 and 2, and we can get that it is equal to g times positive minus divided by 2, so that is equal to positive 0.00 expression 5, and this is equal to negative 0.005, so it's probably that is equal to 0.005, right? That is equal to positive 0.5, right? So that is positive
divided by r is equal to 8. So 8 is here plus x7 is 14 and equation 1 plus 8
Welcome to EDU World Space.
average equals to
So in this question we are given the following statements was it a point that we are studying, right? So it's redirecting in the right direction is equal to 6, right? And the shear strain is equal to 650 into 10 to the power negative 6. And
Welcome to EDU World Space.
so in this question we are given, right? Now what we're going to do over here is that we are going to just write reverse circle, right? Reverse circle theory is going to be of help over here, right? And we're going to take help of the example 6, right? So we can start working on the problem. Now to be able to build a circle we need the axis, right? So this also we are going to use, right? Now what we're going to do is going to have C, right? So after that equation the absolute value of C is equal to the strain in the bridge, right? And that is equal to sum of the strain divided by R, right? And plug in the values and you get that it's equal to 600 right? Now we also need the radius of the circle, right? And that can be found out by the that is under root the difference of the strains divided by 2 whole square plus the shear strain whole square, right? So again you have all the values, you just need to plus them in and you get that is equal to 3.4644, right? Now there is negative 4, right? And that is approximately 46 negative 6. Right, now all we need to do is that we need to draw the graph circle given state of things occurs at point A. So let's first of all take a look at the that is right. Now as you can see over here, right, that these circle strains, right, they are always at point A, and this is the radius of the circle, right? So this is the radius circle, right, that is right. Now what we need to do over here is that the principal strains now they are in the point, right? So we're going to take the help of this circle, right? So principal strains is equal to 2C negative R, and that is 600 minus 6, right, and that is equal to 0.6 into 10 raised to 6, and that is approximately equal to 254 into 10 raised to negative 6, right? Now we need to find out the other principal strains, so that is equal to C plus R, right? So 600 plus 346 plus C into 10 raised to right? And that is equal to 946. 946 right, now what
this question is asking us about voltage at a given frequency. So I'm going to go ahead and write that delta V is 100 volts. So delta max is 100 volts. Then it continues with the sine, asking us T is conductor. This question is frequency about so and capacitor. So And a resistor. So we need basically A is asking us about the resonant frequency. If at resonant frequency, so the most power will be delivered to the resistor.
Right now, since the resonance frequency they have the same sign, right, then the absolute resonance frequency
1 over LC, the resistor. So just putting that into a calculator. Negative 6 power, which by the way, that's the same as 10 to the negative 5th power. So I'm just putting that into a calculator. 224.
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2Q charge and an outer shell of minus 4Q charge, and we're going to find the electric field everywhere. So to begin, we need to write down Gauss's law. Closed line integral with a closed loop integral of dA equals the total charge inside divided by epsilon. Also remember that when we have a point charge, we can say that the electric field equals KQ, total charge inside divided by R squared. K is just a constant, 9 comes into a 9. You can also write it in terms of epsilon, and it is equal to 9 divided by 4 pi epsilon naught. Okay, so let's find the electric field. Alright, so right at this point, inside this inner shell, there is no charge here. If there is no charge, then Q is the H, so the electric field is to 0. What about in between our first shell? A to B.
So I'm just going to put that into a
calculator. In a conductor, the total electric field must be 0. So there's no charge on the inside, and things induced E must also be 0. B less than R less than C, within this first 40 region. Our inner shell has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed is plus 2 hours. So that means that the electric field can be written as a point charge in terms of epsilon or just K. And writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by R squared. Our inner shell has some total charge of plus 2Q. And let's see now. C less than R less than D, so now we're in this outer region. Okay. So if we're in this outer region, I know that electric fields must be equal to 0 here in this region. Because when we're in a conductor, the electric field must be 0. Plus 2Q here, so we need minus 2Q on this inner surface, divided by, but in general, E still 0 there, because we are inside the conductor. Let's see, finally, when we are outside of the system, all we have to do is take the total charge on 3Q plus 2Q is minus 2Q, so Q equals is minus 2Q. And we get E equals 1 divided by epsilon times minus 2Q over R squared. Alright, we can go ahead and graph this.
And when I write E0, I write 0, 0. So this is going to be delta
0 here, 0 there. Between B and C, we see 2 4 pi 0 times minus 2. And now we have to remember one of the properties. So even though that this is a quadratic function, you can get out the graphing calculator and see what happens when you have a negative value outside of your expression.
The cosine would be adjacent
So I'm going to input all of these back to above. Now, to see what happens when you have a negative sign outside the expression, you can get out of the graph. It looks like the side something when you graph it, there will be two solutions. You shouldn't choose the physical solution to see what happens. So in this instance, it will be something like this.
And we need to determine the angular frequency. So let me just keep you right.
Okay, so now we can look at these lines that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be zero on the inside of this guy would be that one diamond. So this diamond is zero. What about on the outer surface? Outer surface must be the total charge on the shell. It's 2Q. Okay, so let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charges in this inner shell. So we need a negative 2Q on that inner surface. Inside of this guy. Okay. And then what about on the outer surface? On the outer surface? On the outer surface, all we have to do is think about, okay, well there's minus 2K right here, surface. We need to have more. What has to be on there?
So I'm going to put that in, and then I'm going to look for the excess.
That's the only way for the net charge to work. And then what about to
R which is 10.
and the outer surface? Okay, so
10 squared. Plus omega. Every case where they say omega, I'm going to write X. So L is 2.
Welcome to EDU World Space.
Okay, so we have two concentric shells, and a radius A, and a radius B of our inner shell, and a radius C, and a radius D of the outer shell. The inner shell has a total charge of plus 2Q, and the outer shell has a total charge of minus 2Q, and we're going to find the electric field everywhere, and where the charges are. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is. Gauss says that the closed, so the integral of E dot dA equals Q, the total charge enclosed, divided by epsilon. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, E is 0, so E must be 0. It's just a constant. Okay, A less than R less than B. Also remember we're in this inner shell, first our smaller shell. This is a conductor. One of the properties is that E equals 0 inside of E dot A. So, B less than R less than C. So now we're in this region. Well, what is the total charge in that region? Q enclosed? Well, just the charge of that inner shell, just 2Q. So, now we can just imagine that it was a point charge and say that the electric field E equals V1
224 was omega 0.
4 pi epsilon times Q, total charge inside, 2Q over R squared.
It is 224.
Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface and summarize here. What is the total charge in here? Well, it must be 0. Why is that? We're inside the conductor. So, E equals 0. There it is. Q. That's not too bad. Now what happens if we are outside of everywhere? So now what happens if we are doing a Gaussian surface outside of this system? Well, what is the total charge enclosed? Plus 2Q minus 2Q, that equals 0.
Times
E is 0 here as well. We can go ahead and grab this. Well, 0, 0. So we have this region to 0. So B to C, goes something like this. It's 1 over R squared. And then it goes straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller shell? So, if we are looking at this region right here, well, we know that the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. It must equal 0. B3, what about the outer? There's something right here. Well, what is our charge enclosed here? Alright, now let's look at where these charges. Plus 2Q. It's over
10 squared, 100 squared, times 10
electric field due to this 2Q charge. So, well, that's 2Q. The electric field must. What about our large shell? We go right on this inner diameter, right here.
C.
We know that the electric field must equal 0. That means it needs to cancel this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at this.
I am not noticing anything.
Minus 2Q. And what about this outer surface? It's got to be 0. We have a net charge of 0 here.
From a different perspective. This was for the power dissipated in the whole surface.
So, the outer must equal 0.
This down here is just for the resistance. So, if I know the current, I sub 0, which is just delta V average, delta V maximum, those are then I can square it. I squared R, and this I'm 5. So this would be just across the resistance 1/2, and delta V max squared over Z squared.
Welcome to EDU World Space.
Times R.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We can put the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of mu dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Gauss's law, and this is our area element. This is our total charge enclosed on our Gaussian surface. This is epsilon 0, just a constant. And E is what we're looking for. So let's look for our first region, which is when we have a radius less than A. So for or less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0.
And then down here, multiply by 2 on both sides is going to give me 500, so I'm going to do delta V max.
Alright, what about if we're in between A and B, so we're in the shell? Well, if it is a conducting shell, then by definition, it must have 0 electric field.
Minus 2.
So we have the same thing. E must equal 0 here. Now what about this cavity between B and
R
C?
squared is 100.
So, for B, less than R, less than C, well now we do have some charges. We have the total charge on this shell is 2Q. It must have 0. Just in general, we know that the formula for the electric field of the point charge, E equals K, which is 1 over 4 pi epsilon, or 99, KQ, divided by R squared, B. We can use this for our region between B and D, and we see that the electric field E equals
And multiplied by
K, Q, which is 2.
Okay, let's see what that gives me.
Q right here is the total charge. R squared, 99 is just KQ.
Almost exactly the same.
Write this more explicitly. Divided by 4 pi epsilon. We can use this for our region times 2Q. Over R squared. Okay. Now what about the region C and D? So now we are in this outer ring.
So here
Well,
we have
when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor.
and then down here we just have
So, for the region between C, less than R, less than D,
was AS.
E equals 0 to Q.
But either way, the answers are
Inside that conductor.
very almost identical.
Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just can use this formula right here for our regular point charge, and we get our electric field E equals 1 divided by 4 pi epsilon 0 times 6Q over R squared. So we're just going to get this formula right here. Those are all of our regions. Now we can go ahead and graph this. So if we wanted to graph it, it would look something like this. We have R, and we have E, and we have A, epsilon B, times D,
40 ohm resistor.
Okay, and we are going to get between regions A and B.
D. And we've got the
And what about between C and D? 0.
between
So if we wanted to graph it, originally 0 is 40 inside of that inner shell. And between regions B and C are rectangular. So it goes as a 1 over r squared.
Is 65.
So something like this. And we see a similar function for when r is greater than d. However, this time
What frequency
we are going to have a different
deliver
front,
250
and
watts of power?
it's going to be a little
Well, power.
and so that's that. Now, what about the charges on the inner surfaces? We see a similar function. Okay, so the inner surface, this is 120 volts, surface
For max, oops, that's delta V RMS.
to be 0. Why is that? Because the electric field is 0 when we have a Gaussian surface. And this guy
Is 120 volts.
now surface object has a charge right there.
RMS
The inside is 0.
This
So,
is going to be
you know,
RMS.
okay, so
Get rid of the one
is
you have
0.
RMS.
And I guess it's
RMS. Okay. Now we want
What about the outer?
this to be 250 watts.
All the outer surface right here needs to contain all the charge for this inner shell. So it has to be
I'm going to
plus
go
2
ahead
here.
and calculate the cosine of 5.
Okay. And what about for our large?
Now, cosine of phi is really just or z. Now, we want this
Okay. The inner. So we do a Gaussian surface right here. We know that we must have a net 0 electric
Okay,
field.
so I am going to have to calculate.
In order for that to happen, there must be an induced negative 2 cube charge inside of here.
Because
So it has to be negative 2 cube. Why is that? Because we need a net to 0. Okay?
over z. So
The outer surface,
RMS
your Gaussian surface, we
ERMS.
know that's just the total charge
Where
equals 2.
right here.
If that happens,
Okay.
and that's that. Also, another thing to know about this graph is that this is, if we were to have units on this, we would expect that this would be taller than this one. Because this is 6 divided by 4 pi 2. That's just the total charge.
So,
Anyways, check.
that gives me 250
And that's that.
is delta VRM squared R over V squared R squared plus 2 L minus 1 over 2 C
Welcome to EDU World Space.
also squared. So let me put that into a calculator. Except I'm going to put it in like this. And I'm going to look for where y is 0. So, C 250 minus C
Welcome to EDU World Space.
squared. Put that in squared. So, R is alright, over R squared, which is 40 squared. plus parentheses 2i minus, wherever I see f, I'm going to write x on. That's blue red, but on. Alright, 2i x times L or square L square 5 plus squares minus square 1 over 2 C, which is 65 the negative 6 power and square root. Okay, so I am seeing a line at 250. And now I'm going to zoom out. There I see little blips in the line. So there it is. Okay. So I get 2 x-intercepts. Okay. I get an x-intercept at 250 equals 2,000. On 3 significant digits, so 2,080 hertz. And I get another frequency at 2,130. Let's look back at the question. Okay, so that's it. It was delivered at 2 frequencies, 2,080 and 2,130. The graph, by the way, looks like this. 2,130 frequency, and this is 2,130. Back in the question. Power minus 250 watts. That's what I do. And so, 230. The graph, by the way, it actually is. The graph, by the way, is it's the same on both sides. So I was looking at this point and this power minus 250 watts. Minus 250 watts. And so so I'll start by drawing a diagram here. And then what I'd like to do is draw, so I'll start by drawing vectors to A, B, and C. So I'm seeing that A is up here, B is over here, and C is down here. So, alright, so let's get the components of UA, UB, and UC. UA vector is looks like it is straight up C3, and then in the negative y direction 0.75. So negative 0.75. So let's get C, J. Alright, so let's get the read Z, E, K. Okay, U, B, straight up, is, let's see, it's got an X component and a Y component. The X component is 2 cosine 4. Negative J, 0.75, and the Y component would be 2 sine 4.
Welcome to EDU World Space.
So in this example, we have an inner shell of a positive 2Q charge and an outer shell of minus 4Q charge, and we're going to find the electric field everywhere. So to begin, we need to write down Gauss's law. Closed line integral of the closed loop integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals kq, total charge inside, divided by r squared, the distance away. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, as it is equal to 1 divided by 4 by epsilon naught. Okay, so let's find the electric field. Alright, so right as this brings point on the inside of this inner shell, there is no charge here. If there is no charge, then Q is zero, so the electric field on this side will be equal to 0.
Then the Y component is negative 1.
What about in between our first shell, A to B? You can also remember that in a conductor, the total electric field must be 0. So, there's no charge on the inside, everything's reduced. B must also be 0. So, B less than R less than C in this first ported region. Our inner shell has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed is plus 2Q. So that means that the electric field can be written as a point charge in terms of epsilon or just as K. And writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by r squared. Our inner shell
going to be B minus
has the total charge plus 2Q. And let's see now, C less than R less than B, so now we're in this outer region. Okay. So, if we're in this outer region, I know that electric field must be equal to 0 here in this region, because when we're in a conductor, the net electric field must be 0. That's plus 2Q here, so we need minus 2Q on this inner surface, divided by r squared. But in general, E still must be 0 there, because we are inside the conductor. And finally, when we are outside of this system, all we have to do is take the total charge on Q plus 2Q is minus 2Q, so Q enclosed is minus 2Q, and we get E equals 1 divided by epsilon times minus 2Q over R squared. But in general, E still alright, we can go ahead and graph this. And finally, and what do we see? 0, 0. So, 0 here, 0 there. Between B and C, we see 2, 4 pi epsilon 0 times minus 2. And now, we have to remember length property, so even though that this is a quadratic function, right, you can get out your graphing calculator and see what happens when you have a negative value outside your expression that you're looking at.
1 squared.
So I'm graphing it now, and I think that all of you should graph it as well.
That'll be in the I direction.
Now, to see what happens when you have a negative sign outside the expression.
J direction.
You get out the bracket.
K direction.
Let's get negative. It looks like you side something like this.
400 times 1.15 square root. 1.25 squared.
When you graph it, there will be two solutions. And the student will choose the physical solution to see what happens. So in this instance, it will be something special.
That gives me 147.
Alright, there we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. So remember, electric field must be visited. There's nothing on the very inside of this guy. Green dot is. So this guy must be 0. What about on the outer surface? Outer surface must be the total charge on this shell. It's 2Q. Alright. Okay, so let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge of this inner shell. So we need a negative 2Q on that inner surface. Inside of this guy, okay. And then what about on the outer surface? Outer surface. On the outer surface, the total charge of
2 cosine 40.
all you have to do is think about, okay, well there's minus 2K right here, surface. We need to have what has to be out there. It has to cancel
2 sine 40 minus
minus 2Q. So we need negative 2Q. That's the only way for the net charge to be like this.
Where?
And then what about to outer surface? The outer surface.
I plus C equals J plus times 2.
Welcome to EDU Workspace.
Okay, so we have two concentric shells, and radius A on radius B of our inner shell, and radius C on radius D of our outer shell. The inner shell has a total charge of plus 2Q, the outer shell has a total charge of minus 2Q, and we're going to find electric fields everywhere, and where the charges are. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant.
2 sine 40 minus
Also remember Gauss' law. Here it is. Gauss says that the closed, so the integral of E dot dA equals Q, the total charge of closed divided by epsilon electric field is given by. Alright, so first region, radius less than A equals 9, okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. It's just
negative 3.
okay, A less than R less than B. Also remember in this inner shell, first our smaller shell, this is a conductor. One of the properties is that E equals 0 inside of the conductor. A equals So the total is 0. B less than R less than C. So now we're in this region. Well, what is the total charge in that region? Q enclosed. Well, just the charge of that inner shell plus 2Q. So now we can just imagine that it was a point charge and say that the electric field E equals B1 divided by 4 pi epsilon. So remember, times Q, total charge inside, 2Q over R squared. There it is. Alright, now we're in our outer shell. C less than R less than D. Well, C less than R less than D. Well, do our Gaussian surface, which is here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So remember, equals 0. There it is. Not too bad. Now what happens if we are outside of everywhere squared? So now what happens if we are doing a Gaussian surface outside of this system? Now we're in our outer shell. What is the total charge enclosed? Plus 2Q minus 2Q. That equals 0. E must equal 0 here as well as the total charge. We can go ahead and graph this. Well, it must be 0, 0. So we have these regions of 0. So B to C. Go something like this. Squared. Now what happens? And then it goes straight back to 0. So now what happens? Alright, now let's look at where these charges might be located. So what is the charge on the inner surface of our smaller sphere, or smaller shell? So if we are looking at this region right here, well, if we know that the electric field must equal 0 here, there's no charge on the inside, which can be induced to the must equal 0. What about the outer? Go right here. Well, what is our charge enclosed here? Right, now let's look at where this charge is 2Q. It's everything. Everything is in there. We have an electric field due to a plus 2Q charge. So we are looking at plus 2Q. About our large shell. We go right on this inner diameter. Right here. Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at this surface. The electric field is minus 2Q. Then what about this outer surface? It's got to be 0. We have a net charge of 0 here. We go right on the inner diameter. Magnitude. Square root. So, and the outer must equal 0. All of the minus 2 squared. 572.8 squared. Then what about this outer surface? 633.6 charge. Let's verify that that's correct. There's no answer in the back of the book. Notice this.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell, and the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We can put the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere.
Welcome to EDU World Space.
259.3.
So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of B dot dA equal the total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Gaussian file, and this is our area elements. This is our total charge enclosed in our Gaussian surface. This is epsilon 0, just a constant. And E is what we're looking for. So let's look for our first region, which is when we have a radius less than A. So for, or less than A, well, we don't have any charge there, so that means that Q equals 0, divided by Q equals 0, E equals 0. So in general, this is this is our area. So E equals 0. This region. Alright, what about if we are in between A and B, so now we're in this shell? Well, if it is a conducting shell, then by definition, it must have 0 electric field. That means that E equals 0. So we have the same thing. E must equal 0 here. Now what about this cavity between B and C? For B,
This time,
less than R, less than C, it is a conducting shell. Well, now we do have some charge. We have the total charge of this shell plus 2Q. So, 0. Just in general, we know that the formula for the electric field is charge. E equals
so we need to figure out
K, which is 1 over 4 pi epsilon, or 99. KQ. Now what about this divided by R squared
is
we can use this for our region between B and C, and we see that the electric field E equals K. We know that Q is 2 Q right here is the total charge divided by R squared. R squared, 99, is just K. We can write this more explicitly. Divided by 4 pi epsilon.
Gamma. No beta.
This for our region times 2Q.
And I'm trying to figure out the magnitude of F.
Now what about the region
F sub
C and D? So now we are in this outer ring. Well, we are in this outer ring. Remember that the electric field must equal 0 because it is a conductor. So, for the region between C less than R less than D, E equals 0 to alpha. Okay, and then finally, what about if we are outside of this subject? So what happens if R is greater than D?
And we also know
well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just can use this formula right here for our point charge, and we get our electric field E equals 1 divided by 4 pi epsilon 0 times 6Q. Well, when R is greater than 0, R squared. So we just those are all of our regions. Now we can go and so if we want to graph it, it looks something like this. So we have R, and we have E, and we have A, B, C, G,
Okay. So I think we got 5 equations, 5 unknowns.
Between regions A and B.
Alpha, gamma,
and what about between C and D?
Alrighty. 0. The unknowns are alpha,
originally 0 because we have no charge inside that inner shell. And between between regions B and C.
So we do have enough.
Because of the 1 over r squared.
Wait.
Something like this. And we see a similar function for when r is greater than d. However, this time we are going to have a different factor in front, and it's going to be
Fourth equation. If I plug all of those in here, it's just going to give me that.
and so that's that. Now, what about the charges on the r squared inner surfaces?
Do have enough.
Well, we see a similar function. Okay, so the inner surface, that's the total charge on the inner surface of the solution.
Let's substitute.
And it has to be 0. Why is that? Because the electric field is 0 on when we have a Gaussian surface, right?
Think about what else we do. We know F's of X. Oh, we know F's of X.
The charge right there, there's a charge inside, is 0. So, inner, well, okay, so inner is 0. And I guess we could use 0. Okay, what about the outer?
So, we don't need these two.
All the outer surface right here
All of these know F's of X.
needs to contain all the charge for this inner shell. So it has to be plus 2q.
So, let's go ahead and rearrange
So what about for our large? 0.
They say cosine of something. So, cosine of alpha.
Okay. All the outer surface of the inner
1.5 over X.
needs to contain. So we do a Gaussian surface right here.
Cosine of gamma.
We know that we must have net 0 electric field.
Now I'm going to substitute.
And with that to happen is that there must be an induced negative 2q charge on the inside.
1.5 over
So it has to be negative 2q.
Where?
Why is that? Because we need a net t for 0. Okay?
Plus
On the outer
1.25
surface,
over X.
so our Gaussian surface,
Where?
we know that that's just the total charge, 4 plus 2.
Rearranging.
And that's that. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be a bit taller than this. Because this is 6 divided by 4, 5, this is 2. That's just the total charge, 4 plus 2. This is a way of checking. And that's that. Also, another thing to note about this graph is that this is, we were to have units on this, we would expect.
Let's see what we get.
Taller.
Welcome to EDU World Space.
1.5 squared. 1.5 squared. Over 1 minus cosine squared.
And that's that.
Of 75 degrees. 2.02 kilonewtons. Let's check. Let's see what we get if that answer is correct. Let's see what we get. What question is this?
Welcome to EDU World Space.
85. That is correct. So now all I have to do is figure out f sub y. And f sub y is just f cosine 75. 0.02. Part now. 85. 523. Is that what I wrote? Yep. Okay, this problem, regardless of what you learned in from this book, this is a simple extension of the Pythagorean theorem here. So I'm just going to write 8 of the total length is the square root of 4 squared plus 2 squared plus 3 squared. And I'm just going to solve it for z. So it's going to be the square root of 8 squared, which is 4. So minus 4 squared is 16 minus 2 squared, which is 4. So it's going to be 6.63 meters. I'm just going to check the answer. Done. It's the easiest question of this unit so far. It's going to be the square root. So it's going to be the square root of 8 squared, which is 4. 8 squared, which is 4 minus 4 squared, 16 minus 2 squared, which is 4. So it's going to be 6.63.
Very close. Today, question number 1. We are looking for the amount of force the skater is using to propel herself with his force. We're going to start this problem out by identifying our known components. The problem they give us mass is equal to 46 kilograms. Also in the problem, we know that we are starting from rest. Conditions against the wall. We know that h1 equals 0 per second. And we know that we have the final velocity of f of, we're going to start this problem out, negative 1.2 meters per second. Now in this case it's negative because we are moving back away from the wall. Assuming that we're facing the wall, moving backwards, we have a negative velocity. This is all done in a time interval delta t of 0 from 1 to h. 0 also is about second. And then in the end, what we're looking for is the force that this skater is exerting. And this is a average force. Also a vector. Now in this case it's negative. So here, what we really have is a change in momentum due to the force acting over a period of time. So we're going to use the impulse momentum database on the page is. This is all change in momentum in a negative velocity equals t. This is all done in a time interval with change in time. Change in momentum always in the end. T final, momentum final, minus momentum initial. Now in this case, we already said that we were starting at 0. Since we're starting at rest, there is no initial momentum. 0. Momentum, remember, from our general equations, it's writing down here. Momentum is equal to mass times velocity. Okay, so here, the square mass times our final velocity. Write that in. Mass, velocity, final. In this case, we already said equals our final momentum. We're going to divide the change in time solve for our force. Divided by delta t. Momentum leaves us with the average force that we are looking for. So we've solved this algebraically. Let's go ahead and substitute in our numbers. Our mass, remember, is 46 kilograms. Velocity, 6 kilograms. Times now our final final is negative 1.2 meters per second. In this case, the negative is important. That y, when we get to an actually answer here at the end, our delta t is 0.2 seconds. We can solve through, so I find that in the end, our force is equal to negative 69 newtons. And again, this negative sign is significant here because
Welcome to EDU World Space.
there we go. Question number 10. We have a stream of water that strikes a stationary turbine blade horizontally.
Welcome to EDU World Space.
And then what we are asked to find is the magnitude of the average force exerted on the water by the blade. One key piece of learning from this problem, or one trick to this problem, what it tells us is mass of water per second that strikes the blade is 30 kilograms per second. So we are going to assume, for our problem's sake, that this is all happening in a 1 second interval. That's going to help us get this out. Okay, let's get started. So we are given in this problem that the water has an initial velocity of 16 meters per second. And when it strikes this blade, then this final velocity is negative 16 meters per second, moving exactly the opposite direction as it's done. And like I mentioned, we're going to talk about this happening in a time interval of 1 second. That allows us to identify the mass of the water that's moving in that 1 second. Initial velocity 30 kilograms. The reason I want to do this is because 16 now can use the impulse momentum theorem to solve this delayed negative problem. You know, impulse momentum theorem is graph delta t, you change in momentum, and that force is what we are looking for. So that is our unknown that allows us to identify the mass. So we have force delta t by delta t over. So that our force equals is E final minus P initial. Now that delta t divided by delta t. Our mass is going to be 30 kilograms because we define this as a 1 second interval. Right out. Remember that momentum equals mass times velocity. So our momentum final would be mass times velocity final. Our momentum initial, mass times velocity initial, divided by delta t. Same both, I can back that out. Which gives us force equals mass delta t final minus the initial. All over the time interval, 30 kilograms, 30 kilograms. Solve this as far as algebraically, and now we're ready to substitute in numbers. Remember that momentum equals mass, which is 30 kilograms. Momentum equals mass times velocity in 1 second. The V final is negative 16 meters per second. Minus
Welcome to EDU World Space.
Which is at positive 16 meters per second. All in minus time interval 1 second. And we get an average velocity of 960.
So, first we have to draw the velocity, and to draw the velocity,
Welcome to EDU World Space.
And then, next one is we that can determine
Number 9,
the original plane
we have this rocket
of the circle
that is space probe, sorry, not rocket. Space probe has a rocket attached to it that is traveling in outer space. This retro rocket is fired to slow down the probe, and we are being asked to find the momentum of the probe after the retro rocket ceases to fire. Okay, so let's start again with what we know. We know that initially,
our original plane,
the space probe has 7.5 space
in more circle,
meters per second of momentum initially. We know that the retro rocket flies an average coordinate of 0, so let's start again, 10, 6, start again, now, this is where the little trick is in this problem. You have to read between lines a little bit the fact that it is a retro rocket, which means it's going to be firing in the opposite direction of the motion. So motion, which has been defined here as positive because of the initial momentum of the rocket. So if the motion going forward is positive, anything going against it would be negative, which means that this force that the retro rocket is applying is a negative force. And then we know it applies this negative force in a time interval of 12 hours. Now, we are asked what is the momentum of the space probe. That's all about is that in opposite direction. So let's look at our impulse motion theorem. Force applied, the time interval that it happens there is equal to change in momentum. Force times t, final, minus momentum initial. In this case, we are looking for momentum final, so we're going to add over momentum initial. Plus, let's look at our T initial. Let's look at our equals what our final momentum will be. Now we can plug numbers in. So 10 to the 6th newtons. Force exerted by the retro rocket, momentum initial done. Minus 12 initial second interval. In this case, we are looking for, add that to, we are looking at initial momentum that the space probe had over 7.5 to the 7th kilogram meters per second. And that equals, and it will be 2.0, 7, 10 exerted by the 6 kilogram per second. So again, in this problem, it was more about understanding where the negative sign comes from. Negative sign is the retro booster in the rocket. So make sure you catch that one. That's all. In this problem, it was more about understanding negative sign. It was more about understanding retro booster in the rocket. So make sure you catch that one. Retro booster in the rocket. So make sure you catch that one.
Welcome to EDU World Space.
So in this question we have been given the state of strain that we are studying, right? So in this the strain acting on the x direction is equal to 3 and resolution is 1-6. Acting on the y direction is equal to 550 into 10 raised to 1-6, right? And the shear strain is equal to -650 into 10 raised to power -6, right? And
welcome to EDU World Space.
The z direction is 0 to positive. So in this question we have direction, right? Now we are going to use the movers circle daily, right? And for that we are going to build the circle, and for that we need the axis, and we're going to use the equation 10.13 from that, right? So we have OC that is equal to the average value of the strains, right? So that is the sum of the strains divided by 2. Right, and we calculate it together is equal to 425 into 10 into 1/6. Right, now all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have underneath the difference of this strains divided by 2, that is 12, plus the shear strain divided by 2 whole square. You have the values, you just need to plug them in, and you get that it's equal to 3.8 to 1. Right, now all we need to do is that we need to put 1 into 10 raised to power negative 4, right, and that is approximately equal to 348.2 into 10 raised to power negative 6. Right, now what we need to do is that we need to drop the circle. Right, so let's take a look at that. And you get that it's equal to 3.4. So now as you can see over here that this is the point A at which the rate of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right, because we take the help of the circle. Now for that, principal strain is equal to OC negative R, right? So you have the values, you just need to plug them in, and you get that it's equal to 67.8 into 10 raised to power negative 6, right? And the other principal strain is OC plus R, right? Again, you have the values, just plug them in, and you have your value. Your answer in no time, right? So we have 770 degrees into 10 raised to power negative 6. Right, so now that we have the value of the principal strain, we need to find out the maximum in plane shear strain, right? That is given by this 6, right? Divided by theta, that's equal to R. Right, so when you shift this to over here, you will get to find out the value of the maximum in plane shear strain, right? So gamma sub maximum in plane, that is equal to R, that is equal to the difference of the principal strains, right? So you have values, you just need to plug them in, and you have your value, that is 696 and 10⁻6. Right, now since the principal strains, they have the same sign, right? They have the same sign. So same sign means that we can directly have the expression for the maximum value of the waves. A shear strain, right, that is maximum the principal strains is equal to 773 into 10 raised to power negative 6. This concludes our solution. Right, now since the principal strains, they have the same sign, right? So they have the same sign. The same sign.
Welcome to the channel. Here we text complex questions and break them down into simple step-by-step solution.
Welcome to EDU World Space.
So let's solve this question. So in this question we have epsilon A equals to epsilon x into cos square theta plus epsilon y into sin square theta plus gamma xy into cos theta into sin theta. Following this, epsilon x equals to epsilon y equals to 0. Substituting the value, we get gamma xy plus 2 be 5.7
Welcome to EDU
10
World
is to the power
Space.
minus 4 2a. So let's first is y1 bar a1 minus y2 bar a2. Doing this we get as way as 0.0653. Now we have tau xy s plus b tau a by I x b by I x b. So tau x है b tau a by 5 by 64 64 minus d4 minus d4 to d minus d. So that means tau xy s plus 3.82 d. Now we have tau xy equals to g to gamma xy. So this is what 38.9297 to b equals to 5.6 to 10 raised to power 6 into 5.7 to 10 raised to power minus 4. b comes out to be 83.05. Tau xy s equals 3.02 d. Now we have tau xy equals to g to gamma xy. So this is 38.
Welcome to EDU World Space.
So in this question, the radius is equal to 15 millimeter, right? The material that is used over here is steel. The tension that is applied over here is of magnitude 2 kilometer meter, right? And we are required to determine the strain along the x dash direction and the y dash direction, right? Now, the thing to note over here is that as there is no load that is being applied over here, right? So it means that if there is no load, so there would be only torsion present. And as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction, and that is equal to 0, right? And if there is no stress, so it means that there is no normal strain, right? So it means that the strain in the x direction is equal to the strain in the y direction, and that is equal to 0, right? So now since this is all cleared up, let's write the strain Rosette equation for 45 degrees, right? The strain Rosette equation for 45 degrees is, and if there is no stress, the strain along the x direction, so it means the strain along the x direction cos square 45 and the strain along the y direction. Sorry. So this is all clear out. Strain along the y direction is 45 plus gammas of xy sine 45 degree and cos 45 degree, right? Now we just discussed that the strains along the x and y direction are equal to 0, so it means that these two terms would become 0, right? It means only liquid system. So solve it and we'll get that it is equal to positive sigmas of x, gammas of x y divided by 6. Right, let's say that this is equation number 1. So now what we need to do is that we need to write the strain of z equation from 135 degree. Now how did we get 135 degree? So 45 and y direction equal to 0, so 0, right? Right, so now what we need to do is that we need to write the Rosette equation for 45 degree. Sorry, we have 135 degree. Now what we have 135 plus z equals y, 135 degree and sine 135 degree. Right? So again, these two terms will become 0 and the only liquid system, and solve it and you will get that it is equal to negative gamma by 2, right? Let's say that this equation of it. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to d times e divided by j, right? And recall that torsion is equal to g times gamma. Now what we are going to do is that we are going to compare these two equations, and we will solve it for gamma, right? And when we solve it for gamma, we will get this expression, right? So what we're going to do over here is that we're going to just plug in the values, and we'll get that gamma is equal to torsion formula 5.6, right, which means 0,050, right? So just plug it back in equation number 1 and 2, and we will get that it is equal to positive 0.050 divided by 2, that is equal to positive 0.0025, and this is equal to negative 0.005 divided by gamma, that is equal to 0.005, sorry, that is equal to 0.005, right, positive 0.025, right? So that it is equal to positive 0.005 that is equal to positive 0.025, and this is equal to negative.
Welcome to EDU World Space.
So in this question we are given the following.
Of course, I'll begin by drawing the diagram.
Right, so connecting the x ratio is equal to 480 into 10 raised to power negative 6. The strain acting in the y direction is equal to 720 into 10
See, there are three forces.
right, and the shear strain is equal to 650 into 10 raised to power negative 6, and
Welcome to EDU World Space.
Which is
0.
vertical.
So in this question we are given right. Now what we are going to do over here is that we are going to use the
And F1 that appears to be in the XZ plane.
circle, right, over circle,
There are three
theory is going to be of help over here, right? And we are going to take help of the example 10.6, right? So we can start working on the problem. Now to be able to build a circle with the excess, right? So
So, since F1 is in the XZ plane, it's shown like
right,
this.
so after that equation,
F1
f
that appears to be in the
value
XZ
is equal to
and right angle symbols aren't in there, but
right, and that is equal
that's
to
what they're showing us.
sum of these three divided by 2, right,
The writers are showing us.
plug in the values and we get that it is
So,
equal to 600 into 10 to the power negative 6.
F1
Right, now we also need
proportion
to build the radius of the circle,
this
right, and that can be found
nine.
by using this equation, that is
So, and that's
under root
the
the difference of the space minus 22 whole square plus
so for
shear strain divided by 2 whole square. Right, so again you have all the values, so now we need to plug it in and you get that is equal to 3.46, right, 4
is going to
negative 4, right, and that is approximately 346 into 10 raised to power negative 6. Right, now all we need to do is that we need to draw the circle, plus what we are going to do is simply
and they are both in the positive direction.
the given state of values at the left point A, so we will bring it angle from that point.
In the
So
negative
let's first of all take a look at the
is negative
right.
150. So now let's get, oh wait,
So as you can see over here, right, that circle given point of strain,
I sorry about that. I was thinking about
F3, and this is the radius of the source code,
Okay,
right?
F2. What are we given about F2?
This is the universal code, like that
We are
twice.
given
Now,
that
what we
its
need to do over here is
projection
that the principal strains are
onto
there in the point, right?
the
So,
XY plane
look at this close-up, right? So, the principal strain
is this
negative R,
direction,
that is 600 negative
6 degrees.
So,
So I like to write
that is equal to 0.6 into 10 raised to power negative 6, and that is equal to
I like to write
into 10 raised to power negative 6, right? Now we need to find out the other principal strain, that is equal to 4 plus R, right? So 600 plus 346
times
4 into 10 raised to power negative 6, right? And that is equal to 946.6.
Again, I can think a little bit. Probably should have memorized this.
946
cosine 60.
Right, now what we need to do is that we need to find out the maximum. Now we need to find out the other in
Alright. Now, F1 in the
so
X
for that we have the expression that makes gamma of maximum in right divided by 4 right? So we can simply just shift the right, and we have
times the in the expression. Sine, nothing matters. Either way. Sine of 45 degrees equals a cosine of 45 degrees and square root 2 over 2. Y direction is going to be the same thing, except cosine.
the difference of the principal strain, right?
They are both
Calculated and get that
positive. So,
6, right, and that is approximately 6 right, now since the principal strains, they have the same sign, right, then the absolute resonance strain would be
we gotta start with the beginning one, 150. And that's going to be sine. 60 degrees square root 3 over 2. So 50.
Right now, since the principal strains, they have the same sign, right, then the absolute resonance
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2Q charge and an outer shell of minus 4Q charge, and we're going to find the electric field everywhere. So to begin, we need to write down Gauss's law. Closed line integral with a closed loop integral of E dot dA equals the total charge inside divided by epsilon r. Also remember that when we have a point charge, we can say that the electric field equals kq, total charge inside divided by r squared. This way. K is just a constant, 9 times 9. You can also write it in terms of epsilon, and then also divided by 4 pi epsilon naught. Okay, so let's find the electric field. Alright, so to begin, right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, A equals 0, so the electric field must also be equal to 0. We can see that the electric field equals 54. What about in between our first shell, A to B? Well, remember that in a conductor, the total electric field must be 0. So, if no charge on the inside can be reduced, E must also be 0. Right in this green spot, B less than R less than C, or in this first 40 degrees region. Our inner shell has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed is equals to between our So that means that the electric field can be written as a point charge in terms of epsilon or just as k. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2q, divided by r squared, our inner shell.
Welcome to the channel. Here we discuss complex questions and charge plus 2q.
And let's see now. C lesson R lesson D. So now we're in this outer region.
Well, at least this diagram
So
is
we're in this outer
easier
region. I
to
know that the electric field must be equal to 0. That means we get
a little bit harder to
in a conductor, the electric field, and that electric field must be 0.
let me go ahead and
2q
draw.
here. So we need
Then
minus
draw
2q on this inner surface divided by r squared. But in general, E still needs to be
Good job of drawing that y-axis.
because we are just going to conductor C now. And finally, when we are outside of this system,
This diagram.
we have 7 which takes total charge from
So, continue this through.
So Q
We've got a point B down here,
and we
which
get
looks
E
like an easy
equals 1
one.
divided by epsilon
Definitely an easy one.
times
Point
minus
A
2q
up here. We're shown that this is 3.
Alright? We can go ahead and graph this.
This is
And
4.
let's see, 0, 0.
This is 2.
0 there.
That's it for that one.
Between B and C.
Oh no. This. We keep 1 1/2. Draw a few 4 points. And then
Now,
there's a point C back here.
so even though that this is
Harder
a
to visualize.
you can get out your graph and see what happens when you have
The hypotenuse is 2 feet. And the angle is 20. So I'm going to green
your expression that you're getting.
this. And I'm going to indicate that this is
To see what happens when you have a negative sign outside the expression. Get out your graph.
and this is 2 sine 20. The hypotenuse is 2 feet.
It looks like
Alright, so the distance from A to B, or you indicate that
when you graph it, there will be
going
two
to be the x direction is going
physical
1
solution. And so in this instance, it will be simple.
in the y direction, it's going negative.
Alright, there we
2
go.
to 3. It's only
Okay,
negative
so
1.
now we can look at the charges that are around these shells. Okay,
In the z direction, it's going down
the
4
the inner surface of our small. Remember, electric field must be inside of this guy, where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge.
So in the x direction, it's going backwards, so it's negative
Okay,
2 sine 20.
okay, on the inner surface, we need to have an electric field 0, so it has to cancel
In the
total
y
charge.
direction,
So we need to negative
over
2 on that inner
2
surface.
plus 2 cosine 20.
Okay,
That would
and
be
then what about on the outer surface?
positive correction.
On the outer surface,
So in the x direction, it's going backwards, so negative
is
well,
okay.
and then in the z direction,
right
it's
here.
negative 2 sine 20.
It has to be out there.
Right.
It's too cute. So we need to negative 2. This is the only way for the net charge to be
We need to figure out the resultant force. So, force AB is going to be FAB vector AB over U. AB. So F AB is going to be,
Welcome to EDU World Space.
FAB, which I did not write down yet, but the book tells us that
shells.
FAB
Radius B of our inner shell. And radius C of
20 pounds.
The inner shell has a total charge of plus 2q. The outer shell has a total charge of minus 2q. And we're going to find the electric
Vector AB, I'm going to use the X component.
So remember that when you have a point charge, the electric field is given by this. Remember what K is?
Over the square root
Equals 9
1.5 squared
times 10 to the 9. It's also equal
plus 4 squared
to 1 over 4 pi epsilon. Epsilon is just a constant.
Okay.
Also remember Gauss law.
That gives me
says that the closed integral of E dot A equals Q, the total charge enclosed divided by epsilon is given by this. Alright, so first we're going to find radius less than A. Okay? So we are right here in this little green dot. We have no charge there. With no charge, E is 0. So E must be 0.
just a negative 4 in the numerator.
Okay, A less than R less than B. We're in this inner shell from first, our smaller shell. This is a conductor. One of the properties is that E is 0 times A. So it's equal to 0. B less than R less than C. So now we're in this first radius.
Now the denominator
The
becomes
total charge in the version we are here enclosed.
FAC according to the book.
So
40 pounds.
now we can just imagine that it's a total charge.
40 times
The electric field equals
on the denominator.
divided by
I'm putting
4 pi epsilon times Q, total charge inside,
negative 2 sine
over R squared. There it is.
squared. Now the denominator plus.
Alright, now we're in our outer shell. C less than A less than D. C less than R less than D. That's what you are Gauss surface. We're seeing over here. What is the total charge in here? It must be 0. Why is that? We're inside of the conductor.
Alright, so the numerator is negative 2 sine 20.
Now what happens if we are outside there? So now what happens if we are...
I'm going to put the 2 plus 2 cosine 20 in the numerator.
What is the total charge enclosed? Plus 2q minus 2q, that equals 0.
27.6.
0 here as well. We can go ahead and graph this. 0.
And it's around negative 4.
Which is 0. B to C. Goes something like this. It's going to go squared. And then it goes straight back to 0.
I need to add those together to get the result.
Alright, now let's look at where these charges might be located. So, what is the charge on the outer surface of our minus our smaller shell? So, if we are looking at this region right here, well, the electric field must be 0 here. There's no charge there inside. Here's the
27.6 minus negative 4.6.
Go right here. Well, what is our charge?
23.
Goes here. Where these charges? That's 2q.
16.2
field due to plus 2. It's 2q. What about our large shell?
And
Go right on the
done.
same diameter. Right here.
27.6
Okay. We know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land on the surface. So minus 2q.
That ain't no calculus.
Then what about this outer surface, it's got to be 0. You have a net charge of 0 here. So, the outer must equal
Down. Check if that's the correct answer. Yes, it is. And then to get alpha, beta,
Welcome
and
to
gamma,
EDU World Space.
there's cosine.
Okay, so for this problem, we have the inner shell and the outer shell.
1.97.
And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B. The outer shell is bound by the radii C and D. We can put the electric field everywhere and see if we can find where the charges are going.
80.
So let's go ahead and look at the
Welcome to EDU World Space.
Beta.
So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of the delta A
Change the numerator to negative 46
total charge that is enclosed in our region divided by epsilon 0. So in general, this is our find and this is our area element.
And here's our current.
Surface is epsilon 0, just expected, and E is well. So let's look. We're going to write down Gauss's law for our first region, which is when we have radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q divided by equals 0, E equals 0.
So you really do need to read the last sentence. X equals Y. And so, this is a very simple problem.
Just read it. Alright, what about if we are in between A and B, so we're in the shell? Well, it is a conducting shell. And by definition, it must have 0 electric field. So, the same thing. E must equal 0 electric field. Now what about this cavity between B and C? Right? So, for B, less than R, and C, well now we do have some charges. The total charge on this shell plus 2q must have, so, just in general, we know that the formula for the electric field and the point charge, E equals K, which is 1 over 4 epsilon, or 99. K field divided by R squared. We can use this for our region between B and C, and we see that the electric field E equals, just in general, K, formula for the electric Q, which is 2. Q right here is the total charge divided by R squared. R squared is just we can write this more explicitly.
So you really do need to read the last sentence, which says that X equals Y. And so, this is a very simple problem again. Like 90 is a little bit harder.
Now what about the region C and D? So now we are in this outer ring. Well, we are in this outer ring. Remember that the electric field must equal 0 because it is a conductor. So, for the region between C, less than R, less than D, E equals 0. Okay. And finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have a total charge enclosed, which is 4Q, 2Q, 6Q. So we just see this formula right here for 19.5 point charge, and we get electric field equals Y, which is equals 1 divided by 4pi, so epsilon 0 times 6Q over R0, which is 4Q, 2Q, 6Q, 6Q. So we just see this formula right here. Those are all the regions now. So if we wanted to graph it, it would just be like this. Here we have R, and
again, drawing the diagram and figuring out what it means is most of the battle.
D,
Y,
and we are going to get
X, and we need to continue the Z axis downward. We're given F1, which appears to have no X component. That's going to be
and between regions.
So it's a 3, 4, 5 triangle, but it's got no X. Y,
something like this.
Y,
and
okay.
we see a similar function
F1,
this time we are going to have
F2 has all 3 components,
and it's going to be
here. These angles are directly given.
Now, what about the character on inner surfaces? Well, we see a similar function.
I guess because book does.
So,
and the angle with Y is 120. So yeah, they're all directly given. So let's go ahead and do F1.
Why is that? Because
F1 in the X direction F1 in the Y direction is, well, it's going positive Y direction, 3/5 of 450. I guess well, 45 divided by 5 is 9. 9 times 3 is 27, so that's going to be 270 newtons in the positive direction. F1 is going to be 4/5
all the outer surface right here,
450, but it's in the negative direction. So that's going to give us negative 360
this inner shell.
So let's move on to F2. This is actually all pretty straightforward. F2 is just going to be the 525 and the cosine of X direction is going to be alpha, which is 45.
So we do got some surface right here.
Y is
we know that at 0
cosine of the Y direction, 120 degrees.
The only way for that to happen is that there must be negative 2 charge inside
525.
Why is that? Because we connect
cosine of Z, which is 60 degrees.
on the outer surface.
So this Y one should end up giving us a negative number. The other one should be positive.
That's just the
Let's
total
put
charge
that into a calculator. 120 degrees. Sine of the Y direction. 525. Sine of 45.
Also, another thing you know about this problem is that this is, if we were to have units on this,
525 cosine 120.
Taller.
Negative 6 divided by 1.5. And 525 cosine 60. Put them into A. It's just going to give us 262.5. Okay, so now we have to add them together. Adding the x components, well, there is only one x component. So that's going to be, so I'm going to write it in vector form.
Welcome to EDU World Space.
371.2 I F. So now I'm going to do 270 minus 262.5. Just going to give us, just going to give us 270 minus 262.5. 7 and a half. Now we have to add them together. So now we have to add them together. Plus, so that's going to be 5j, and then in the k direction we've got negative 360 plus 262.5. So now I'm going to do 262.5 divided by negative 97.5. 7 we need to sketch the vector and find the magnitude. Well, sketching the vector is what I would do next. We've got 371 in the I direction. Then we've got 7.5, which is almost nothing. It's the J direction. And then we've got a negative K direction. So it's going to be like down over there. Maybe something like this. We need to sketch the vector. Sketching the vector. All right. Sketching the vector is what I we've got. So now 371 in the I F sub 1. We've got 371 squared. Then we've got 7.5 squared plus negative 97.5 squared. Set the calculator. So now 384 alpha negative 371.2 over 384. Beta and gamma are going to be very much the same. Inverse cosine over 2 over 384. Beta 371.2 over gamma are going to be very much the same. That's the bar. 14.8. Let's put 7.5 in the numerator. And negative 97.5. Inverse cosine 100. Now I'll check the 14.8.
the channel where we tax complex questions and break them down into simple step-by-step solutions that solve today's problems together.
Alright, now for the easier question, we need to figure out the coordinate direction angles for F1. So that's going to be, hey now, where that's red.
Now check the
Alpha.
Now check the
1. Beta 1. And with the Z direction, gamma 1. So, alpha 1 will be the inverse cosine. Oh, wait a minute. I forgot to get the magnitude. F1. Oh, wait. We know the magnitude. It's 60. Silly. Alpha 1. Alpha 1 is the inverse cosine and with the Z direction of F1x, which is negative 19.3 root 3. Oh, wait a minute. Cosine. Oh, wait a minute. To get the magnitude. I forgot to get the magnitude. Over 60. We know the magnitude. We know the magnitude. 60. Silly. Just, it's just 19.3. Alpha 1 is alpha cosine and gamma 1. F1x, which is gamma 1. Negative 46. So just putting them into a calculator, it's just 19.3. It's just 19.3. And gamma 3, 60, 124, negative 46. Negative 46. Positive 19.3. So that would be 1.2.
Welcome to EDU World Space.
Negative 46.
So in this example, we have an inner shell of positive 2Q charge and an outer shell of minus 4Q charge. And we're going to find the electric field of the break. So, to begin, we need to write down Gauss's law. Clothesline integral,
Comes to the channel where we tax complex questions and break them down into simple step-by-step solutions that solve today's problems together.
Field equals KQ.
Well, at least this diagram seems easier to see.
You can also write in terms of epsilon.
It's a little bit harder to interpret, though.
Okay, so
let me go ahead and draw what I can draw
right
here.
at this green spot, we are on the inside again in our shell. There is no charge here. If there is no charge, then Q is 0. So
Poor job of drawing on the y-axis. Let's try it again. So, continue this through. We've got a point B down here, which looks like the easy one. Definitely the easy one. There's a point A up here.
B less than or less than C, or less than region.
And we're showing that this is 3.
Has a total charge that is 2Q.
This is 4.
And so that's what would be Q enclosed here. So
This is 2.
is plus 2Q. So that means that the electric
That's
field
it for that one.
charge
Oh no. This is 1 and a half. These are feet.
Epsilon 0 times the total charge inside, which is 2Q.
There's a point C back here. It's harder to visualize.
And let's see now.
But the hypotenuse is 2 feet. and the angle is 20. So I'm going to green this, and I'm going to indicate that this is
minus 2q on this inner surface.
2 cosine 20.
But engine 1 E still
and this is 2 sine 20. The hypotenuse is 2 Alright, so the distance from A to B for you is going to be, when the x direction is going 1.5 feet, is 2 cosine 20. In the y direction, it's going negative 2 to 3, so it's only negative 1 foot.
0 there.
In the z direction is going down 4 feet. AC.
Now, even though
A to C, A to C. When the x direction is going backwards, so negative 2 sine 20.
outside
In the y direction, it's going over 2 plus 2 cosine 20. That would be positive direction. X direction is negative, and then in the z direction it's just negative 2 sine 20. Alright.
when you graph it, there will be 2 solutions. You can choose the physical
We need
solution.
to figure out the resultant force. So, force AB is going to be FAB.
Alright, here we go.
U vector
Okay, so now we can look at the directions.
over U.
Show. Okay,
F
let's look at the inner surface of our small. The inner
is
surface
going
of
to
our
be,
small.
let me put this into a calculator,
Remember, electric field must be
FAB, which I did not write down yet, but the book tells us that FAB
outer surface
is 20 pounds. Times U vector AB, I'm going to use the x component, negative 2, nope, for AB, not BC, so 1.5 over the square root. 1.5 squared plus 1 squared plus 4 squared. 20 pounds. 20 pounds. Okay. That gives me 6.84 I. I'll put negative 1 into the numerator. 4.56 J. Put negative 4 in the numerator. 18.2K. F.
Welcome to EDU World Space.
So now the denominator becomes, well, first of all, FAC, according to the book, is 40 pounds. So it's 40 times.
Inner shell.
Now in the denominator, I'm putting
So
-2 sine 20.
Point charge. The electric field is given by this formula. K
2 plus 2 cosine 20
times 10 to the 9. It's also equal to 1 over 4 pi
plus 4 squared. 40 times.
Also remember Gauss law.
The numerator is -2 sine 20.
It says that the closed integral of e dot
-4.27.
Alright, so
Now I'm going to
first
put the
region,
2 plus 2
radius
cosine 20 in the numerator.
Okay, we are right here in this little green dot. We have no charge there. No charge. That means 0. So E is positive. Okay, A is an
And now -4.
inner shell. Also remember this is a conductor.
I need to add those together to get the resultant. 6.84 minus 4.87.
So now we can just imagine that
1.97 I
equals
27.6 minus 4.6
times
1.56 23
squared. Alright, now we know how to
18.2 plus 48.5.
What is the total charge in here? Well, it must be 0. Why is that?
And we're still not done. 27.6.
Now what happens if we are outside of that? So now what happens if we are moving
This equation.
well, what is the total charge close? Plus 2q minus 2q.
Now you'll calculate.
That equals 0. We can go ahead and graph this. Charge 0, 0. So that means 0. B to C, right here. Because something like this is
52.1 Newton.
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller shell? So, we are looking at this region right here. Well, the electric field must equal 0 here. There's no charge on the inside. There's nothing to do.
Check if that's the correct answer. Yes, it is.
Go right here.
And then to get alpha, beta, and gamma, we just use the inverse cosine of FR X, which is 1.97, over FR, which is 52.1. Putting that in the calculator.
About our large shell. We go right on this inner diameter.
Check if that's the correct answer. Check if that's the correct answer. 87.8 degrees. Beta. Have to change the numerator. 23. Gamma, I change the numerator to -46.7.
What about this outer surface? It's got to 0. We have a net charge of 0. We got a large shell. We go right on the inner diameter.
And those are correct.
So the outer.
Pretty challenging. So I'm going to begin by drawing and understanding what's going on here.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. So we can put the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the area line integral of E dot dA equals the total charge that is enclosed in the region divided by epsilon 0. So, in general, this is our Gauss's law, and this is our area element. This is our total charge enclosed in the Gaussian surface. This is epsilon 0, just a constant, and E is what we have. So let's look. So, for our first region, which is when we have a radius less than A, which says, so for, I don't know why we're less than A, well, we don't have any charge there, so that means that Q equals 0, E equals 0.
So I'm just going to go ahead and say right now, gamma 1 is going to be 90 degrees.
And this is also Alright, what about if we are in between A and B, so we're going to show right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field. So we have the same thing. E must be 0. Now what about this cavity between B and C? So, for B, this one R, and C, well, now we do have some charge. We have the total charge on this shell, plus 2q. So, just in general, we know that the formula for the electric field is charge, E equals K, which is 1 over 4 epsilon, or 99, KQ. Now what about this? Divided by r squared.
F2y.
We can use this for our regions of E equals C, F, and we see it equals field E equals 2Q. So K, 400 general, Q, which is 2. Q right here is the total charge divided by r squared. R squared, which is 1/3, is just 99. Write this more explicitly. 1 divided by 4 pi epsilon. We can use this to Q for over r squared. Okay. Now what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must have 0 because it is a conductor. So, for the regions between C and R plus D, E equals 0. Inside that conductor.
F1.
Okay. And then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge of which is 4Q plus 2Q, 6Q. So we'll just use this formula right here for our zero point charge, and we get the electric field E equals 1 divided by 4pi. Finally, what about if we go outside?
So FRX
Epsilon 0
is going to be
times 6q
all the x's.
over r squared.
Y is going to be all the y squared. So that would be
So there we go.
F2y.
Those are all the origins. Now we can go ahead and graph this. So if we wanted to graph it, it would be like this. We have R and
30
the E
plus F1
and we have A, B
in the y direction.
times 6q.
Well, if alpha 1 and beta 1 are
Okay. And we are going to get between A and B. And what about between C and B?
And so, nevertheless, in the y direction
Originally,
is
0
going to
would
be
be a charge inside of that inner shell. And between regions B and C, there's a
we want
so because of the 1 over r squared, so you can do this, and we see a similar function for when r is equal to d. However, this time we are going to have a different prefactor term, and it's going to be inside that.
Alright.
And so that's that. Now, what about the charge volume? So the surface line is r squared. Well, okay, so the inner surface.
F1 is no longer
Inner surface this time.
in the xy plane.
It has to be 0. And why is that? Because the electric field
Oh,
is
note
0
that
on
realize the xy
Gaussian
plane. I thought we were
surface.
telling F1 was
Sky.
Alright.
So that's the surface.
So,
The charge right there, the charge is inside, is the
So, now,
inner.
this,
Inner.
after a zero sign, beta 1. Okay.
There we got the outer. Well, the outer surface right here needs to contain all the charge for this inner shell. So that's 2q. Okay. And what about for our large?
Which is going to be F1 in the Z direction.
Okay. The inner, the outer surface right here. So we do a Gaussian surface right here. We know that we must have a net 0 electric field. The only way for that to happen is that there must be an reduced negative 2q charge on the inside right here. So it must be negative 2q.
Great, F3 has an extra.
Why is that? Because we need a net t equals 0. Okay?
Alright.
On the outer surface, or Gaussian surface, that's just the total charge, 4 plus 2 plus 6 is 0.
So, how am I going to figure it out?
Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be a bit taller than this. Because this is 6 divided by 4, 5, this is 2. That's just the total charge.
The reason why is I'm not sure that I know the relationship
And that's that.
between gamma 1, no, alpha 1.
Also, also another thing to note
Beta 1.
is that this is the original
And gamma
respect
1.
taller.
Welcome to EDU World Space.
This is 60.
So I looked back in the book and I noticed that the cosine squared of plus the cosine squared of beta 1 plus the cosine squared of gamma 1 equals 1. I did not recall that.
Welcome to EDU World
So,
Space.
now, since I know my gamma, I know anyway, we'll figure this out. FRX is that, FRY is that, FRC is that. And so, I need to find out, now I know, after 1, we're saying that negative 350 is F1Z, which is also going to be F1. I need to find cosine gamma 1. So isn't that in green? Okay. It's going to be a lot of equations, I think. F R. So we're saying that negative 350 is also going to be F1. Oh, wait a minute. FR only has cosine gamma, a Z component. X and Y components are 0. So now I could use these two equations. Nope, that's not going to give it to me. Because I've got 3 unknowns. If I use these 3 equations, oh wait a minute, then I've got 4 unknowns. This would mean that I have to use these 4 equations. 4 equations. 4 unknowns are 0. So now, if I can combine some of them together, then I can simplify it. So let's just go with the last 3, second one. This one. That's going to say that the cosine of gamma 1 is negative 350 over F1. Cosine gamma 1 negative 350 over F1. Okay, good. Then I can simplify. You know what? I could solve all of this for cosine of alpha 1, cosine of beta 1, and cosine of gamma 1. Let's go ahead and do this. That's going to say that cosine of gamma 1 cosine of alpha 1 equals 400 sine 30 sine gamma 1 over F1 from the first equation. Cosine alpha 1 equals 400, okay good, sine 30 so F1, okay good. Cosine beta 1 is going to be negative 200, no, it's going to be 200 minus 400 cosine 30, 400 sine 30, 400 sine 30. Over F1. I can substitute all of it to the last equation, and that's going to give me negative 350 over F1 squared plus 200 minus 400 cosine 30 over F1 squared. I can substitute plus 400 sine 30 over F1 squared 1. Then multiply by F1 squared on both sides. And I can get rid of all of these and just say that that equals F1 squared. And so I can take the square root of both sides, and that would be what F1 is. So F1 would be, put it in here, a lot of work, square root, negative 350 squared plus 200 minus 400 cosine 30 squared plus 400 sine 30
Welcome to EDU World Space.
squared. That gives me 429. So let's see if this is right. 71. Yes, it is. Except it's not in these.
Welcome to EDU World Space.
So now I just need alpha, beta, and gamma, and that should be pretty easy now that I know that that's 429. So, the inverse cosine, let's see if this is right. Alpha is going to be 400 sine 30 over F1. So that's 429. So alpha is going to be 62 degrees. Beta is going to be the inverse cosine, but on numerator, I need to put 200 minus 400 cosine 30. 200 minus 400 cosine 30. It's going to give me 110.
So for the question 1,
and gamma is just going to be negative 350 and 60. And that would be obtuse. 145. Let's check those answers. And that is correct. I'm a little bit surprised that I didn't make any mistakes. That was pretty complicated. The gamma
touch the origin.
is just going to be negative 350. It's going to be negative 350.
Then draw 6 bit circle of color
in here. That would be 1
this one
of the 3/4 check. However,
this part will be
you're basically going to have to
the absolute maximum
factor.
So,
Y
it's just that absolute
and
maximum
so
is equal to epsilon 1.
trying to see what's going on. I think I may try to do this directly.
Welcome to EDU World Space.
First we have to draw the law circle, and to draw the law circle we have to determine the center.
Welcome to EDU World Space.
Which I always talk about. And then the next step is we have to determine the original point of the circle, which can be found by epsilon x.
Okay. So let's try to get FDA first. I see that in the X direction,
that's our original
I see a lot of so
for the
what I'm going to do is from B to A.
In more circle, it will be
if we start here and go until we get to the Z-axis, then we can see that the distance this distance here is 3 plus 2, which is 5 feet. So UBA, vector from B to A, is going to be, well, it's going negative 5. The eyes. It is going 6. Here. This distance here is in the J direction. And it's going upward. They're all doing the same thing as the J direction. They're all going up 14. Well, from C, X direction, it'll be negative in the X direction, negative 3. And it's going upward, and it's going upward. This distance here, negative 3. In the Y direction, positive y-axis, and in the Z direction they're all the same. Well, from X negative negative X direction, negative 3 is from B to A. This X here has to go Y direction.
plus is operator of the circle.
Let's go back to BA. From B to A, you have to go negative X direction. Or from C to A, X direction, you have to go positive. This should have been positive. You gotta think about whether I messed up my negatives or positives. So let's go back. From B to A. B to A. X should be negative. Y should be positive. Z should be positive. Good. C to A should be positive X, positive Y, positive. Let's go back to B. Okay. From B to A. From B to A right now. Negative. From C to A. From X to A. It is going negative in the X direction. So this distance here is 5.
Welcome to EDU World Space.
So in this question we have been given the state of stream that we are exploring, right? So in this the stream on the x direction is equal to 300
Y direction is also going
acting on the y direction is equal to 550
negative 6.
Right? And the shear strain is equal to negative 650 10 raised to 5 negative 6, right? And that's it.
Welcome to EDU World Space.
Direction, right? Now we are going to use the
I'm going to do
circle
this.
theory, right?
Force.
And for that, we are going to fill the circle and for that we need the x's and we will do
350 times
right? So we have AC that is equal, right? Average value of the
over
right? So once that
let me get that.
right, and then
Calculator.
Right now, all we need to do is that we need to find out the radius of the circle, and we have the expression for the radius as well, right? And we have understood the difference of the circle trains divided by 2 is plus the shear strain divided by 2. We have the value of the
It's going to be negative 5
yes, that's equal to 3.4
over
1
square root of 5 squared.
So now we need to do integration to power number 4. So that is approximately equal to 3 of the times 2 into 10 raised to power negative 6.
And so,
Right, now what we need to do is to graph the circle. Right, so let's take a look at that.
I'm going to check the answers to make sure I'm on the right track. It's going to be negative 5. Yep.
So now as you can see over here that this is
Negative 109i.
at which the
Now all I have to do is
state of
put
strain is occurring, right? So we need to measure the angle from this point, right? So
31j.
now the physical strains are easy to find, right? Because using the units of the circle. Now for that, physical strain is equal to 14 right? So we have the values which are from the range and we get that equal to 57.8 meters per year to power negative 6, right?
I can
And the other physical strain is OC plus R, right? Again, you have the values from the limits and you have the values from this. You also
So for
use
C, denominator,
into denominator
3 squared.
right, now that we have the values of this square, we need to find out the maximum in place, right, shear right, that is given by this
FCA
divided by 2, right, that's equal to R, right, so when we shift this to over here, we will get to find out the value of the maximum
and the
equation
numerator is
right,
3.
so
So for C,
gamma become maximum of 3, that is how many are, that is plus half values.
There's also 3 in the J direction. 100
value that is 6 times
and then the K direction is
right now, since the principal streams they have the same sign, right? They have the same sign. The same sign means that we can
and let's get the last one.
directly have the
So negative 5 squared is 25.
a shear strain height that is maximum
6. And 14 squared is 6. The force is also P direction. FPA is 400. And the numerator is negative 5. 400 gives me. And let's get this one.
Welcome to EDU World Space.
Second numerator is
So let's
negative
solve
6.
this question. So in this question we have epsilon A equals to epsilon x
Negative 100
here stuff plus epsilon y into minus here stuff plus gamma xy stuff
And 14 again.
right stuff. Doing this epsilon x equals to epsilon y equals to 0. Substituting the value we get gamma xy equals to be 5.7.
Check the answers.
Or minus 4.
Welcome to EDU World Space.
This is problem 95.
So let's go minus 5 bar and then doing this we get 1 way as 0.1 0653. Now we have tau xy plus s gamma x plus u a I
don't know what's going on.
I arrange it as tau and then e y u a by 60.
My answers aren't even close.
64 is to be 4 minus b4 minus
Answers?
minus
Negative
b
52
no
plus
second
1.
tau x y
Negative
s
106.
plus equal to e. Now we have tau x y tau x y
What did I do wrong?
tau gamma
On
x y so this is about 38.97
So DA
plus 5.6
go through exactly what I said.
5.7
From D
minus
to
4 E comes out to
going
be equal to 0.5 minus
negative 6 and negative 52 is negative 1. It's only going to negative 2. It's going negative 2 in the x direction. It's
Welcome
going
to EDU
negative
World
6 in
Space.
the y direction. That's
So in this question, the radius right, material that is shown over here is d. The intention that is applied over here is of magnitude 2 kilometers meter, right? And we are required to
so
determine
DA is 2.
speed along the x dash direction and the y dash direction, right? Now,
2 squared is 4.
over here is that as there is no load applied over here, right? So it means that if there is no load expression, torsion present, and as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction, it
Second
means
one
the
is
stress in the y direction, that will
negative 6, I believe.
0, right? And if there is no stress, so it means that there is no normal strain, right? So it means that the strain in the x direction is equal to the strain in the y
Hey, let's see if that is it.
direction, 0, right?
And I'm in question 95.
Now, since this is
Negative
all
52,
clear up, let's write the
So my error was in
and after is 45 degree, right?
This is not
Strain
5.
equation for 45 degree is 0, right? And strain is along the x axis, right? Strain along the x direction positive 1.5
Yes.
and
And distance left to plate was 5. The distance confused too with these two.
Strain of desired direction and 45 plus gamma of x minus 5 now just discuss that the strains about
Now I don't understand why 66 comes after 65. 66 is so much easier. I already have the components of F1. And so, if I want the angle, all I have to do is write alpha.
Sorry, gamma of x minus
Is the inverse cosine of negative 106.1 over F1. Theta would be the inverse cosine of 106.1 over F1. And gamma is the inverse cosine of 259.8 over F1. And we know that F1 is 300. So let me put those in the calculator.
So again, these two terms
inverse cosine of 106
and solve it and get that it is
1 over 300.
Negative gamma by now
9.3.
Now what we need to do over here is that we are going to
change the numerator to negative
formula 1.6, right, which is
get
target maximum is equal to d divided by j, right? And because that target is equal to d by j. Now what we're going to do is that we are going to compare these two equations and we'll solve it for gamma, right? And if we solve it for gamma, we'll get the expression, right? So what we're going to do over here is that we're going to just plug in the values and we'll get that gamma is equal to right? So this bucket back in equation number 1 and 2. We'll get that it is equal to positive
It's the continuation of the previous problem. And they're actually only asking us for the two forces acting at point A. So I don't need to do anything with this. All I have to do is add these together. F resultant is going to be negative 648 I. They cancel each other out in J. And they're actually in K 195.
Welcome to EDU World Space.
390. So, the resultant is just going to be the square root of negative 648. Where it was 390. Putting that in the calculator.
Now what we're going to do is that we are going to right first
negative 648. The 90
is going to be of calculator, right?
Where it is center root.
If you take care of the example
648. 56, and what are my units?
Now we'll be able to build
I hope this is correct. Check. 97. Yep. So now alpha, beta, and gamma. Obvious. Alpha is going to be the inverse cosine of negative 648 over 756.
Right now, we also the radius of the circle, right, and that can be found by using that is under root
negative 4
difference of the
over
right, so again you have all the values, we just
149 degrees, beta is going to be 90 degrees because there's nothing in the y-axis.
Right, now all we need to do is that we need to multiply
gamma is going to be, you need to put 390 in the numerator. 59 degrees. We begin by drawing a diagram as usual.
This is the normal circle right after this, right? Now, what we need to do is that principal space, there is a point, right? So, we're going to take one of the
Okay.
right? So, principal space
We got a force in this direction.
Now we need to find out
Right. We're told that F, okay, 350I, we got a force, minus 250J, minus 450K. And we know that the length right here is 9, right? Meters, right? So the first thing that I want to do is I want to find the direction of the force. Minus 2, which is just going to be the force. And we know that divided by the magnitude of that length here is 9. So the first thing that I want to do is I want to find the direction. So let's go ahead and get that. So just going to be this force. It's just going to be 350. Over the square root. 50 squared.
Right now, since the principal streams they have the same sign, then the actual length of the would be
squared. So that gives me a component of 0.562. Now I'm going to put negative 250 in the numerator. Negative 0.402.
Welcome to EDU World Space.
And I'm going to put
So in
negative
this example, we have an
450
inner shell
right
with positive 2q charge and the outer shell with minus 4q charge. And we're going to find the electric field.
0.73.
So to begin, we need to write down Gauss's law. Closed line integral with a closed loop interval
If I
is
take
dA equals the total charge inside divided by epsilon naught.
U
Also remember that when we have
multiplied by
we
9.
can say that the electric field equals KQ, total charge inside divided by r squared. This is layer. K is just a constant
That
right
will
density
give
to
me
the
the
You can also write it in terms of the
distance.
epsilon that and just divided by 4 pi epsilon naught. Okay, so let's find the electric field.
XY
So, let's
would
write
just
this
be
as
the
well.
XY and Z coordinates
There is no charge here.
point
If there is no
A,
charge, then Q is 0.
except it would be the opposite of the XY and Z coordinates.
Also remember
So X is just going to be 9 times 0.562. Y is just going to be 9 times negative, nope, opposite.
There's no charge on the inside, so nothing's reduced. E must also be 0. B less than R less than C.
It's going to be 9 times.
Our inner shell has a total charge of plus 2q, and so that is what would be Q enclosed here. So Q enclosed is
0.40.
So that means that the electric field can be written as
E is just going to be 9 times 0.723.
writing it like that, we get
Calculator?
times the total charge inside, which is 2q, divided by r squared.
6.51. And what are our units here?
And let's see now. C less than R less than D, so now we're in this outer region, okay? So if we're in this outer region, I know that electric field must be equal to 0 in this region. Because when we're
3.61 meters.
plus 2q here, so we need minus 2q on this inner inside.
Negative 5.06.
Still
Let's check that in the book.
and finally, we are outside the system.
5.06.
All you have to do is take total charge
3.61.
So Q is minus 2Q.
6.51. So the only difference is the book writes that X is positive, but I wrote that X is negative.
Times minus 2Q. So R is 2Q.
I guess they're showing X to be the opposite direction of the X axis. And so, okay, that makes sense. Very good.
There, between B and C. You see,
So the only difference is the only difference is the book writes that X is positive.
and now, we have to remember running properly, so even though that this is what you can get out your drop and
Okay, so let's define any situations to get into one side. On the background, we can see that the chain A and horizontal axis is 40 degrees, and the angle between chain C and the horizontal axis is 60 degrees. Now let's calculate the horizontal and vertical components of the forces. For chain AB, horizontal component is FAX equal to F8 times cos of 30 degrees, which is equal to 200 times cos of 30 degrees, that is 150 times root 3. Similarly, we have vertical component FAY equal to F8 times sine of 30 degrees, which is equal to 300 times sine of 30 degrees, that is 150 Newton. And for chain CD, its horizontal component is FC equal to FC times cos of 60 degrees, that is 350 times cos of 60 degrees, which is equal to 125 meters. Similarly, we have vertical component FCY equal to 125 times
There we go. Okay, so now we
the forces in Cartesian vector form, force AB in Cartesian vector form is
okay.
150 times square root of 3 pi plus
The interceptors are
150
small.
J Newton, and force AB in Cartesian vector form is G equal to
Inside of this guy,
5 plus 105 times root 3 J Newton times.
What about on the outer surface? Outer surface must be the total charge on the shell. Okay, so the large one. Okay, so on the inner surface, we need to have one down to total charge negative 2q.
Now, at least this diagram seems easier to see. It's a little bit harder to interpret. Let me go ahead and draw, at least what I can draw here.
Is, think about, okay, well there's minus 2q right here.
Watch out, we're drawing the y-axis. Let's try again. Okay, so continue this through. We've got a point B down here, which looks like the easy one. Definitely the easy one. There's a point A. Go ahead and draw up here. Is what I can draw here. And we're showing that this is 3. This is 4. This
Welcome to
is
EDU
2.
World Space.
Okay, I guess that's it for that one. Okay. Oh no. This is 1.5. These are all feet. And then there's a point C back here. It's harder to visualize.
So remember,
but the hypotenuse is 2 feet and the angle is 20. So I'm going to green to 9. It's also this. When I'm going to indicate that this is 2 cosine 20. And this is 2 sine 20.
Alright, so first region, radius is less than 3.
Alright, so the distance from A to B,
we are right here in this little green dot,
or U
charge there, with no charge, you will say,
is going to be, in the X direction is going 1.5 feet.
We're in this inner shell, so there's the inner shell. This is
In the Y direction,
conductor, one of the properties is
it's going negative. And this from 2 to 3, so it's only negative 1 foot.
no in this first one. Alright, so, well, what is the total charge in that region?
So the Z direction is going down 4 feet.
So, now we can just automatically point charge. Say,
AC. From A to C
times Q.
A to C. Or in the X direction is going backwards, so negative 2 sine 20.
Alright, now we're in our outer shell. C is C
In the Y direction is going over 2.
What is the total charge?
Plus
in here?
2 cosine 20. So that would be positive direction.
You know what happens if we were outside of this direction? So now what happens if we are...
And then in the Z direction is just negative 2 sine 20.
Well, what is the total charge of this shell? Plus 2q minus 2q equals 0.
resultant force. So, force AB is going to be FAB,
And then it goes straight back to 0.
U vector AB
Where these charges
over U.
which is the larger
So F AB is going to be, let me put this into a calculator,
well, the electric field must
FAB, which I did not write down yet, but the book tells us that FAB is 20 pounds.
what is our charge here?
Times U vector AB. I'm going to use the X component, negative 2, nope, AB, not AC, which is 1.5 to be over the square root of 1.5 squared plus 1 squared plus 4 squared. 20 pounds. 20 pounds. Okay.
That means
that gives me 6.84 I. I'll put negative 1 into the numerator.
we have a net charge of
4.56 J. Put negative 4 in the numerator. 18.2K. F AC. So now the denominator becomes, well, first of all, FAC, according to the book, it's 40 pounds. So it's 40 times.
Welcome to EDU World Space.
Now in the denominator,
Okay, so
I'm putting
inner shell and an outer shell. And the inner shell has a charge of the outer shell.
negative 2 sine
The
20
inner shell is bound by the
squared. Now the 2 plus 2 goes up
everywhere.
20
And see if we can find where the charge is going to.
squared.
So let's go ahead and look
Plus 4 squared is 60. 40 times.
So,
Alright, so
we're going to write down the
the numerator is negative 2 sine 20.
We got the closed line integral, we can type
It's
dA.
negative 4.87. I'm going to put the 2 plus 2 cosine 20 in the numerator.
So in general, 2 is
27.6. And now negative 4.
which is radius of So 4 less than A. Now
Add those together to get the result.
means that 0.
6.84 minus 4.87. 1.97 I.
Right, what about if we are in between
27.6 minus
well, if it is a conductor
4.6.
then by definition, it must have 0.
Add those together to get the result. 18.2 plus 28.5 minus
Now what about this calculator between B and C? Right, so
and we're still not done.
C is well, now we do have some charge. Total charge of the shell plus 2Q. It must have 0. Just in general, we know that the formula for the electric field
This equation
E K, which is 1 over 4 epsilon 99. KQ, divided by R squared. We can use this for our region between B and C, and the straight field D.
52.1.
K, root. Q, which is 2. Q right here is this whole charge. K, R squared, is just
Knockdown.
write this more explicitly. 1 divided by 4 pi epsilon.
Check if that's the correct answer.
Use 2Q.
Yes, it is. And then to get alpha, beta, and gamma, we just use the inverse cosine.
C.
Of FR X, which is 1.97, over FR, which is 52.1. Putting that in the calculator now.
So, for the region between C, less than R, less than D,
Check if that's the correct answer.
E equals 0.
Check if yes, it is the answer. 87.8 degrees.
And then finally, what about if we were outside?
Beta. Just have to change the numerator to 23. 7.
Oh, when I was reading D,
Gamma, I changed the numerator to negative 46.7.
so we just see this formula right here for our regular charge E, and we get our electric field E.
And those are correct.
Finally, 1 divided by 4 times 6Q
To 23.
over R.
Change the numerator to negative 46. Gamma, I changed the numerator to negative 46. We've got
Those are all the regions. Now we can go ahead and get. So if you wanted to graph it, it looks like this. Originally, 0 inside of that and between regions B and C. So it goes as a 1 over R squared plus this, and we see a similar function for R squared and C, but this time we are going to have a different K-factor in front, and it's going to be a loosely side of that. And so that's that. Now, what about those arguments? Well, see a similar function. Okay, so the inner surface is negative 26. Well, times 0. Why is that? Because the electric field is 0 on the Gaussian surface.
26.
The charge right there, which is just inside.
F2.
So, inner.
Simplifying plus
inner 4 is 0. Okay, what about the outer?
That's correct.
all the outer surface right here needs to contain all the charge.
Oh, so far this
Or
section
this inner
is
shell.
exactly
So
the
it has to
same
be
as
plus
the
2
previous. So, what is different? Seriously.
Okay. What about
So, we're showing that this is 30 degrees. We're also showing that this down here is 45 degrees. But I would rather mark this as 45 degrees. And it would be 45 degrees because all it's at right angles.
So if you do a Gaussian
The
surface
magnitude and direction of the result.
we know that we must have a net 0 electric field.
And the x direction.
The only way for that to happen is that there must be a reduced negative to Q charge inside C. So that's the negative C.
Force result in the y direction
net T
is going to be for
outer surface
30 minus
or Gaussian surface. We know that that's just the total charge. 4 plus 2 plus
the resultant force is going to be the square root of f of x squared plus y
Also,
squared.
another thing to note about
And
this
the
graph
thing
is that this is, I mean, we're to have units on this. We would expect that this would be taller than this.
put all of these into a calculator.
This is 6 divided by 4
First two,
by
you know exactly where that theta is, whether it's downward or upward horizontal. And so,
and that's that.
go into a calculator. And 400 plus 30 plus 100 times 45, 912.
Welcome to EDU Workspace.
400 sine 30 minus 8 downward sine 45. And so, negative 366. Square root. First one, 912 squared plus
Welcome to EDU Workspace.
squared is 983 negative 5. And theta is the inverse tangent of the second one on the y direction. Over the x squared. Negative 22 and 21.8 degrees. So we're supposed to measure clockwise from the x-axis, so that would be so are my answers? Let's check. 983 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction. So we're supposed to measure. We've got 3 forces. We're supposed to measure clockwise. So they're drawn with their tails connected together, which is the easiest for me. My answers, let's check. Yeah, it would be 1. And F2. We've got 3 forces. We've got 3 some angles. And F2. Okay. And F2. We need all three forces in Cartesian vector form. So, F1 is going to be angles. It's going to have an x component, which is going to be 50. X direction is the 3 direction. Okay. Y component is going to be, we need all three forces in Cartesian vector form. So we need all three forces in Cartesian, and it is north. So F2 is it's going to have an x component, which would be negative. It's going to have an x component 80 sine x direction degrees, z direction. X direction is 3 direction, and also negative in the y direction. Negative 80 y cosine 15. It's also F3 is x component 30 in the x direction. X component negative sine nothing in the y direction. Sine. Alright. I think I'm going to leave it like that. Also negative in the y direction. And also determine the magnitude of the resultant force and the direction. The resultant force F3 in the x direction is F3. X direction. 3/5 of 50. That's only going to be 30. Minus 80 sine 15. I think I'm going to leave it like that. Determine the magnitude of the resultant force and the direction. Determine the magnitude of the result. 50 times 4/5 is just 40. The resultant force is minus 3/5 80. No sign. 3/5 of 50. That's only going to be 30. Let's go ahead and get that. Sine minus 15. 30 minus 15 sine plus 15. 50 times 4/5 is 40. 50 times 4/5 is 40. 40 minus 80 cosine 15. Let's go ahead and get that. We do the Pythagorean theorem, so I'm going to type in the square root of the first one squared, or x squared plus ry squared right? 54.
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field everywhere. So, to begin, we need to write down Gauss's law. Closed line integral of the closed loop integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals kq
43 degrees
divided by r squared.
clockwise.
K is just a constant, 9 times 9. You can also write it in terms of epsilon, and it is equal to 1 divided by 4 by epsilon large. Okay, so let's find the electric field. Alright, so
54 newtons.
right against green
That's
spot, we are on the
45.
inside of this inner shell. There is no charge here. If there is no charge, then Q is 0, so the electric field must also be equal to 0.
I don't know, so far this section seems to be exactly the same as the previous section.
What about in between our first
What is different? Seriously. So, we're showing that this is 30 degrees. We're also showing that this down here is 45 degrees. But I would rather Mark this was 45 degrees, and
our inner shell
would be 45 degrees because it all
has
right
a
angle.
total charge of plus 2q.
The magnitude and direction
would be q
of the resultant force as well.
So that means that the electric field can be written as a point charge.
X direction is going to be 30 plus 800 sine 45.
Times the total charge inside
Force result in the
is
y direction
divided by
is going to be 30
and let's see now. C less than R less than D, so now we're in this power region. Okay. So during this
the resultant force is going to be the square root of F squared because when we're in the y squared and the thing here is
so we need a minus tangent on this inner surface. But in general, still there.
Let's put all of these into a calculator. It's important that you do the first two, so that you know exactly where that theta is, whether it's downward or upward or horizontal. And so, going to a calculator, and 400 minus 30, 912.
Alright,
Put all of these into
let's go ahead and graph this.
Okay, next one.
And what do we see?
400 sine 30 minus 800 sine 45.
Between C and C.
Negative 366. 4 square root.
Now,
First one.
we have to remember what it's property, so even though that this is a quadratic function,
Squared.
you can get out your graph
One.
and see what happens when you have a negative
Squared is
outside
983.
of C.
And theta is the inverse tangent
So I'm graphing out and I think
of the second one, or the y direction.
to see what happens if you have a negative sign outside of the expression.
Over the x direction.
It looks like
Negative 22 and 21.8 degrees. So we're supposed to measure
when you graph
clockwise.
it, there will be two solutions. So you're going to choose the physical solution to see what happens. And so in this instance, it will be something.
983, 21.8. Yeah, it would be positive 20.8 as measured in the clockwise
Okay,
direction.
so now we can look at the charges that are around these shells. Okay, let's look at one inner surface if we're small. The inner surface
welcome
of
to
our
this
small.
video solution.
Remember, electric field must be 0. Inside of this guy is where that green dot is. So this guy must be 0. What about on the outer surface? Outer surface must be the total charge of the shell.
And gamma is
Okay,
so based on this, you have to calculate the magnitude of it.
okay, on the inner surface,
clearly
we need to have an A equal to 0, so it has to cancel the total charge from this inner shell. So we need negative 2Q. And then what about the other surface? Is think about this 2Q right here must be all there. Minus 2Q. So we need negative 2Q. That's the only way we can net charge to
Welcome to EDU World Space.
Okay, so we have two concentric shells, and a radius A, a radius B of our inner shell, and a radius C, a radius D of our outer shell. The inner shell has a
I don't know, so far this section seems to be exactly the same as the previous section. Don't know what is different, seriously.
Let's get started.
So we're shown that this is 30 degrees. We're also shown that this down here is 45 degrees. But
equals 9.
I would rather mark this as 45 degrees, and
It's also equal
it would be 45 degrees because no, it's a right angle. What's the magnitude and direction of the resultant force? Well,
also remember
force resultant in the x direction is going to be 430 plus 800 cosine 40. Force resultant in the y direction is going to be
charge there with no charge.
400 sine 30 minus 800 sine
less than R less than B. We're in this inner shell, first or smaller shell.
The resultant force is going to be the square root of Fr x squared plus F y squared, and the angle is going to be the inverse tangent of y over Fr. Let's put all of these into a calculator. It's important that you do the first two, so that you know exactly where that theta is, whether it's downward or upward or horizontal. And so, going to a calculator, and 400 cosine 30, 900 cosine 45, 912. Okay, next one. Well, 400 sine 30 minus 800 sine 45 negative 366.
We are outside of it. So now what happens if we are 3,000 circles?
Square root. The first one
plus 2q minus 2q, that equals 0.
Squared plus second one.
We can go and graph this. 0, 0.
Squared is 983. And theta is the inverse tangent
Alright, now let's look at where these charges are.
of the second one, or the y direction.
So if we are looking at this region right here,
over the x direction.
electric field must 0 here, there's no charge inside, there's no charge.
negative 21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be correct. Those two are my answers. Let's check in the book. 983 plus 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction.
This relative has 4 different forces. Force 1, force 2, force 3, force 4 actually gives us the magnitudes and numbers for each of these. It tells us that force 1 and force 2 form 3, 4, 5 triangles with the x and y axis. And so using these, we have to actually find the resultant force vector and show that the resultant force is 0. So we do this by determining the x and y components and summing each of them individually to see that they both add up to 0. So let's start with the horizontal component, or the x component. Because we have all the magnitudes, and we can determine the components based on these 3 from 5 triangles, we can measure each of these triangles individually. So this one right here is the triangle that F force 1 forms with the y and x axis. And this triangle, to the right side, we have to actually find this one force 1 force 2 that forms with the x and y axis. So let's start with force 1. So for the force 1, we're summing each of them independently to see we're going to be using right angle trig. So SOHCAHTOA. So to determine the horizontal component, what a purely horizontal component is. Because we have all the here because to find the horizontal side or horizontal component, we use cosine in SOHCAHTOA, which is adjacent over hypotenuse.
The electric field everywhere, and see if we can find where the
times 4 and 5.
So let's go ahead and use
1 force 2 plus, and here it's going to be SOHCAHTOA once again, and it's going to be 3 over 5. So it'll be 6 kilonewtons, because that's a magnitude of F2,
which says that the
and we can just add actually just subtract force 3 and force 4. Because if you want to see the diagram, both numbers are in the opposite direction horizontally, and actually it's F1 and F2 are.
And this is
if you do this math real quickly, you actually see that this actually all adds up to 0. So we know that overall our horizontal component comes out to 0.
for our first dimension, which is doing a radius of
force 1.
So 4
times
our triangle, and we will find the charge differences. Means that zero
sine. Sine is opposite of hypotenuse, so it's actually going to be 3 or 8 times 3 over 5. And since this force is heading down, I'm actually going to add a negative in front of it.
Alright, what about
next we have to add force 2.
Well,
once again, look at this triangle, and
by definition.
So we do sine, opposite over 0 hypotenuse here is also always 4 over 5. It's going to be 6 times 4 over 5. And once again, looking at our diagram, we actually see that there's actually no 3 or 2 times 3
now what about this?
right? But just horizontal lines pointing towards the left. So we're actually going to stop here and check if these add up to 0. That's what they do. So, force 2 both of these components add up to 0, so we know our resultant force is 0.
K, which is 1 over 4 epsilon, which will 99. K here.
Actually see that. Forgot
about our square. We can use this for our regions inside, and we see that the electric field E is K, Q, Q right here is the total charge divided by R squared. R squared here is just times 2Q, which means this okay, now what about the region C and D? So now we're on this outer ring. Well, we're in the outer ring. Remember that the electric field must be 0 because it is a conductor squared. So, for the region between C and D, E equals 0. Inside that conductor. Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D and D? Well, when R is greater than D, then the rate charge which is 4Q, 2Q, 6Q. So we just use this formula right here for our regular C charge, and we get our electric field E equals 1 divided by 4 pi. Finally, epsilon 0 times 6Q over R squared. These are all of our regions. Now we can go and graph it. So if we wanted to graph it, we have R and we have 1A.
We've got two equations, two unknowns. I'm going to solve the second one for
okay, and we are going to get between regions A and B. And what about between C and D?
Substitute that in the first equation.
Originally, 0 inside of that inner shaft. And between regions B and C, so because of the 1 over R squared, this, and we see a similar function for when R is greater than D. This time, we are going to have a different prefactor in front, and it's going to be a little inside. And so that's that. Now, what about the charge forming inner surfaces?
So the tangent of theta,
okay, so the inner surface, which is the inner surface, this time it has to be 0. Why is that? Because the electric field is 0, and we have a Gaussian surface right here. So this guy is surface, and the charge right there, there's no inside. Now, what about the charge?
700,
So, inner
tangent of theta, and then I want to do the inverse tangent of that, so I can get theta.
0. Okay, so okay, what about the outer? All the outer surface right here.
answer is plus 1.
It needs to contain all the charge.
Okay, so now I can substitute this back into this equation. Figure out what S sub B is. 700
And what about for
930 over cosine of 960.
So we do a Gaussian surface right here. We know that we must have a number.
Alright, we don't have any numbers here, but we're still going to calculate.
The only way for that to happen is that there must be an reduced negative 2q charge.
So we've got F1 here.
So it has to be negative 2q.
We've got F2 here.
Why is that? Because we need E net to
There's
0.
an angle phi. And I'm not going to draw the result. But
Gaussian surface.
the force,
That's just the total charge.
the result of force in the x direction is just going to be F2 plus the x component of F1, which is F1
And that's that.
cosine.
Also, another thing to note on this graph is that this is, if we were to unit this,
Just going to
we would
be
expect that
F1
this would be
sine phi.
taller
F2 does not have a verse. So the
6 divided by 4
is going to be square root of F2 plus the force. 1, the result is pi.
and that's that.
Squared plus x component of F1 sine phi.
Also, another thing to note is that this
And
is
theta is going to be the inverse tangent of
Welcome to EDU World Space.
sine phi, that's phi over F2 plus F1 cosine 1, and we're done. Check the answer. Where? Yep. Sine phi. Looks like they did multiply that out and simplify the Pythagorean theorem here. Let's see if we can do it. Sine phi. Multiplying the first one. Again, one gives me F1 squared plus F1 F2 cosine 5, and there's going to be 2 of them. Plus F1 squared. Wait a minute, that's 2 squared theorem here. Cosine squared of 5. Let's see if we can do it. Plus F1 squared sine squared of 5. But sine squared of 5 plus cosine squared of 5 is 1. So then I'm going to get R is square root of F2 squared plus putting these two together to just get F1 squared plus 2 F1 cosine squared of 5. Yes. So that could have been something. F1 squared sine squared of 5. Alright, so we're looking for some components, and this is question number 39. Well, 39, we really only have 2 components. One going this way, which is not, strangely enough, the x direction. And we have the x and y directions like this. This is the y direction, and this is the x direction. 45 degrees. is number, which by the way would make this 45 degrees also. And then we have F2, but F2 I would prefer to this way, because I like to draw them tail to tail, the X direction. And we have the X and Y directions. This is the Y direction, and this is the X direction. Let's think about what's going on here. Considering where 30 degrees is on the drawing, it would be this. And then we have, and that's going to be F2. This way, F2, which is 150 degrees. Yep, that makes sense. Okay, so components. Let's see here. F1 considering going to be 200 times the sine of 45 degrees, which is just the square root of 2 over 2. That makes sense. Okay. I direction. And the same thing in the J direction. Let's see here. F1. Okay, F2 is going to be, well, in the X direction is going to be the cosine of 30 degrees, and the cosine of 30 degrees is the square root of 3 over 2. So this is just going to be 150, whoops, negative 150, because it's going in the negative direction, in the J direction. And the sine of 30 degrees is 1/2. Is going to be, well, the J direction. In the X direction is going to be cosine. Alright, so simplifying these, square root of 3 over 2. This one is just going to be 100 root 2 I, 100 root 2 J, and the sine of F2 is going to be negative 75 root 3 I, comma, 75 J. This one is just going to be 100 root 2 I.
About length to what? Problem involving three forces, F1, F2, and F3. Has to find the magnitude direction the resultant force, and that's measured from this x prime axis. So we actually have the magnitude and angle of all of these forces actually to find the magnitude and angle of the force. We just have to sum each of the horizontal and vertical components separately. So first, F1, we know is 300 newtons. We're just told that. We're also told that the angle it forms with the x prime axis is 10 degrees. So that's this angle right here is 10 degrees, which is F1, and this angle right here is 6 degrees. So in total,
Welcome to EDU World Space.
The y-axis forms a 20 degree line with the x-axis. On the other side, we have force 2 of 200 newtons, and that's just for the straight orbital. So finally, our third force is 180 newtons, and there's 300 newtons, which is equivalent to a 5, 12, 13 triangle. That force with the negative x-axis, so 5, 12, 13. So we're going to go ahead and just sum all of our x and horizontal components. So for F1,
Welcome to EDU Workspace.
300 times cosine of 20 degrees because cosine in this case corresponds to force 2 x or horizontal magnitude. For F2 we actually don't even have a horizontal magnitude, it's directly upwards. For F3 however, we will be subtracting because this force is going in the other direction, or the opposite direction as force 1. And here, instead of using cosine, because we have the 5, 12, 13 triangle, we can just use trigonometry for right triangles. SOHCAHTOA, in this case, cosine adjacent over the hypotenuse, which is common. This right here is going to give us F2 actually have triangles. For F3, however, this force is going in the other direction, the opposite direction. This force is for y, for the vertical. Instead of using force 1, we use sine. Trigonometry for ratio 26. This time we actually do include force 2, which is 200 newtons. Once again, it's purely upwards. This right here is 500 times the same sine, which is so, or opposite of hypotenuse, so 180 times 5 over 13. This one is the magnitude. The absolute maximum is 389. So, next, we have to find the angle that forms positive To do that, we can use this simple. Theta is going to equal arctan y component over x component. So we just plug in those values. Calculator with theta 9.
Welcome to EDU Workspace.
That gives us the theta value. Remember, this angle is actually the angle between the resultant vector and the x-axis. What we need to do is the angle between the resultant vector and the x prime axis. So remember, theta here, or sorry, the angle between the x prime axis and force 1 is 10 degrees. So if we add that to 20 degrees, then we know F1 forms positive x-axis.
Welcome to EDU Workspace.
Subtract 30 degrees from this, giving us the original 42. 7 degrees. Those are our final answers. This angle is actually the angle between the resultant vector and the x-axis, the force vector. Magnitude 44 newtons in force of 42. Remember 7.1 man here, or the angle between the x-axis and force 1 is 10 degrees. So if we add that to 20 degrees, then we know F1 forms positive x-axis.
That's our original plane. And for the new plane, which will be 30 degrees clockwise from the original plane. In more circle, it will be 60 degrees counterwise. In fact, point Q. So this is not exact. Our original And for epsilon y, it will be at this point. Two. You know that this angle is 85, and so that makes this angle, and for vertical y go down 3. So almost this x1 x that is this is the radius cause that angle careful and thus the same way of 4 with 6 and for the top there's the radius that angle sine angle whole and 9 single as just that angle. And it will be minus 6, which will be minus because it's in the upper half of the circle. Now, for epsilon y dot, it is the center minus the radius cos 4.09, which is minus 116 minus 6. And these are the answers. Now, epsilon y dot center minus radius.
Welcome to EDU World Space.
So in this question we have been given the state of strain that we are studying, right? So in this, the strain acting on the x direction is equal to 300 into 10 raised to the power negative 6. Acting on the y direction is equal to 550 into 10 raised to the power negative 6, right? And the shear strain is equal to negative 650 into 10 raised to the power negative 6, right? And the strain that is acting in the z direction is 0 because there is
Welcome to
that is
EDU
acting in
World
the z
Space.
direction, right? Now we are going to use
So in this
the
question we
Mohrs
have been given the state of strain that
circle,
right? So in this
theory,
strain acting on the
right? And for that we are going to go to the circle, and so for that we need the axis, and we are going to use the equation 10.13 for that, right? So we have OC that is equal to the average value of the strains, right? So that is the sum of the strains divided by direction, right? Right, and you can immediately get this equal to 1025 into 10 raised to the power negative 6. Right, now all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have under root the difference of the circle strains divided by 2 whole square plus the shear strain divided by 2 whole square. You have the values, you just plug them in, and you get that's equal to 3.4, 3.8. Welcome to by 2, 1 to 1 into 10 raised to power negative 4, right, and that is approximately equal to 348.2 into 10 raised to power negative 6. Right, now what we need to do is we need to draw the circle. Right, so let's take a look at that. Here's 3 divided by 2 whole square. You have the values, you just plug them in, and you get that equal to 3. So now as you can see over here that this is the point A at which the rate of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right? Because we'll take the help of the circle. Now for that, principal strain is equal to OC negative R, right? So you have the values, you just need to plug them in, and you get that is equal to 67.8 into 10 raised to power negative 6, right? And the other principal strain is OC plus R, right? Again, you have the values, just plug them in, and you will have your value, your answer in no time, right? So you have 773 into 10 raised to power negative 6. Right, now that we have the value of the principal strain, we need to find out the maximum in plane shear strain, right? That is given by this divided by 2, that's equal to R. Right, so when we shift this to over here, right, we can easily find out the value of the maximum in plane shear strain, right? So your answer is gamma of maximum in plane, that is equal to R, that is equal to the difference of the principal strains, right? So you have values, you just need to plug them in, and you'll have your value, that is 696 into 10 raised to power 6. Right, now since the principal strains, they have the same sign, right? They have the same sign, so same sign means that we can directly have the expression for the maximum value of the strain, gamma, shear strain, right? That is maximum, that is the principal strain, and it's equal to 773 into 10 raised to power negative 6. This concludes our solution. That is 696 into 10 raised to power 6. Right, now since the principal strains, they have the same sign, right? They have the same sign, so same sign means
Welcome to EDU World Space.
So let's solve this question. So in this question we have epsilon A equals to epsilon x into cos square theta plus epsilon y into sin square theta plus gamma xy into cos theta into sin theta. Following this, epsilon x equals to epsilon y equals to 0. Substituting the value, we get gamma xy equals to be 5.7 into 10 raised to power minus 4 UA equals to y1 bar a1 minus y2. So let's solve this question. So in this question, we get UA as 0.0653. Now we have tau xy square s plus b gamma xy by I x t by I x t. So tau x is doing this epsilon tau a by I by 64. Substituting the value, we get 64 plus minus d4 to d minus d4. So that means tau xy s bar plus 3.82 b bar. Now we have tau xy s tau xy equals to c to gamma xy tau xy. This is what 38.957 into b equals to 5.6 into 10 raised to power 6 into 5.7 into 10 raised to power minus 4. B comes out to be 83.05 minus b, that means tau xy
and
s
2 and 1 divided by
now here
divided by
now we have tau xy
square
is equals to c
z1 divided by
Welcome to EDU World Space.
and further and 1 divided by
So in this question, the radius is equal to 15 millimeter, right? The material that is used over here is steel. The tension that is applied over here is of magnitude 2 kilonewton meter, right? And we are required to determine the strain along the x-dash direction and the y-dash direction, right? Now, the thing to note over here is that as there is no load that is being applied over here, right? So it means that if there is no load, so there would be only torsion present, and as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction, is that is 0, right? And if there is no stress, so it means that there is no normal strain, right? So it means that the strain in the x direction is equal to the strain in the y direction, that is equal to 0. Right, so now since this is all cleared out, let's write the strain rosette equation for 45 degree, right? The strain rosette equation for 45 degree is the strain 0, right? And direction is no stress. Strain along the x direction cos 45, and it means that strain along the y direction, sorry, 0, right? Strain along the y direction times 45 plus the gamma of xy is equal to 45 degree and cos 45, right? Now we just discussed that the strain along the x and y direction are equal to 0, so it means that these two terms would become 0, right? And we solve the liquid system, so solve it and we get that it is equal to 0, right? Positive gamma of x y divided by 2. Right, let's say that this is equation number 1. Now what we need to do is that we need to write the strain of that equation on 135 degrees. Now how did we get 135 degrees? So 45, now we just discussed that
So simply start summing up all of
right, so 0, right? Now what we need to do is that we need to write the rosette equation for 45 degrees. So we have gamma of x y. We have 135 plus cos 135 and sine 135 degrees, right? So again, these two terms will become 0 in the immediate system, and solve it and we'll get that it is equal to negative gamma by 2, right? Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to d times e divided by g, right? And we call that torsion is equal to g times gamma. Now what we are going to do is that we are going to compare these two equations and we will solve it for gamma, right? And when we solve it for gamma, we'll get this expression, right? So what we're going to do over here is that we're going to just plug in the values and we'll get that gamma is equal to
Now what we need to do over here is that we are going to 0.0056, right? So just plug it back in equation number 1 and we'll get that it is equal to and we call that positive 0.0056 divided by 2, that is equal to positive 0.0025, and this is equal to negative 0.005, right? So that is equal to 0.005, right? That is equal to positive 0.005, right? So this is like it back in equation number 1. We'll get that it is equal to positive 0.005.
Welcome to EDU World Space.
So in this question we are given the point in the screen at the point that we are studying, right? So this predicting the x ratio is equal to 483 to 10 to 6. This predicting in the y direction is equal to 720 into 10 to 156, right? And the shear strain is equal to 650 into 10 to the power negative 6. And the strain is equal to 0.
Welcome to EDU World Space.
Right? Now what we're going to do over here is that we are going to use the mover, right? Circle.
I don't know, so far this
Right,
section seems to be exactly the same as the previous section.
Theory is going to be
Don't know
help over here, right?
what is different,
and
seriously.
we are going to take help of the example.
So, we're showing that this is 30 degrees.
Right,
We're
so
also
we can
showing
solve
that
with
this
the
down
problem.
here
Now to be able
is
to build a
45
circle, we need the
degrees.
excess, right?
But I would rather mark this as 45 degrees,
Right,
and
so after
it
that
would be
is
45 degrees because well, it's a right angle. What's the magnitude and direction of the resultant force? Well, action seems to be exactly force, resultant,
plug in the values
x direction, what is this going to be? 400, so, force
right,
in
now
30
we also
trace, 800 sine
right,
here.
and that can be found out by
Force resultant in the y direction is going to be rather 400
difference of the values
sine
right
30 minus 800 sine
first rate divided by
magnitude direction of the resultant force.
right, so again you
The
have
resultant force is going to be the square root of FRX squared x direction. F is going to be y squared. And the 30 angle is going to be the inverse tangent.
Right, now all we need to do is that circle.
Put all of these into a calculator. It's important that you do the first two so that you know exactly where that theta is, whether it's downward or upward from the horizontal. And so the resultant force is going to go into a calculator.
So let's first of all take a look at the
400 cos 30, 800 sine 45, 912. Okay, next one. Put all of these into 400 sine 32, right? Sine 45. Down negative 306. Square root. 400 first one. 912. Second one. Where is 983? And theta is the
that is plus R, right? So 600 plus 346, right? Right? And that is equal to 946.
Over extra.
946 into 6 divided by 6. Right, now what we need to do is that we need to find out the maximum
21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be...
For that we have 600 gamma plus
my answers, let's check. The book. 983. 21.8. Yeah, it would be positive 20.8 as measured in the clockwise direction.
This is 9 over here, right, and we have our value, right, now we have gamma.
Alright, this is really a continuation, although this is simpler than problem 63. I do have my coordinates vectors, which is this. This one's going to be in the I direction, the J direction, and this will be in the K direction. So I need to express each as a
right now, just the vector trees, they have the same signs, right?
I'm going to create some room here by erasing a lot of this stuff down below. Vectors. Easier said than done. This is going to be in the I direction, J direction, and this will be in the K direction. Let me get there. Delete. Okay. I'd also like to do this. Express each as
Welcome to EDU World Space.
Okay, so F1
So in this example, we have an inner shell of positive 2p charge and an outer shell of minus 4.
80 cosine 30 cosine 40. So let me get what that amounts to.
So to begin, we need to write down Gauss's law. Closed line integral with a closed loop integral of b dot dA equals the total charge inside by
sine 40 at the end.
Also remember that when we have a weak charge, we can say that the electric field is kq, total charge inside, divided by r squared. This is the way. K is constant, 9 times 10 to the 9. You can also write it in terms of Gauss's law, divided by 4 divided by 4. Okay, so let's find the electric field. So right at this green spot on the inside of this inner shell, there is no charge here. If there is no charge, then Q is 0, so the design integral is also equal to
53.1 I.
Also remember that we need 0. What about in between?
And that is in the positive x direction.
A to B.
In the J direction?
In a conductor, the total field must be 0. So, there's no turbulent inside, we can do so E must also be 0 here. Okay, so let's B less than or less than C, and this first 4 degrees our inner shell
4.5J
has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q
and then it's going in the positive K direction.
So that means that the electric field can be written as a about
and then that's just going to be 130.
Writing it like that, we get divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by r squared, b less than or less than c, our inner shell. And let's see now, c less than r less than d, so now we're in this outer region, okay? So, in this outer region, I know that electric field must be equal to 0 here in this region, because when we're in the conductor, the electric field must be 0 plus 2Q here, So we need a minus 2 Q on this inner surface. But in general, E still equals T0 there. Because we are inside the conductor. And finally, we are outside, and this is simple. All we have to do is take the total charge times 1Q plus 2Q is minus 2Q. So simply make those as minus 2Q. And we get E equals 1 divided by 2 epsilon times minus 2Q over R here. So we need minus 2Q.
5, 12, 13 triangle.
Alright, we can go ahead and graph this. And what do we see? 0, 0. And finally, 0 here. 0 is there. Between B and C, we see
300 times cosine
2.
F2 we actually don't even
And now, you have to remember one of the properties, so even though that this is a quadratic function, you can get out your graphing direction, right? And see what happens if we have a negative value outside your expression that you're working with. So I'm graphing that, and I think all of you should graph as well. To see what happens when you have a negative sign outside of your expression. Even though this is a function, get out your direction. And it looks like
for the vertical this time we actually
when you graph it, there will be two solutions. Make sure that you choose the physical solution. And so, in this instance, it will be something like
sine, so
Alright, there we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0. There's nothing on this very inside of this guy, whatever dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell, that is 2Q. Okay, let's look at this large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge from this inner shell. So we need a negative 2Q inner surface. Remember, electric field must do that. Okay? Inside of this. And then what about on the outer surface? So, on the outer surface, all you have to do must be the total charge on the shell. Is think about, okay, well there's minus 2Q right here. Let's look at this large one. What has to be on their surface? We need to have minus 2Q. It has to cancel the total charge. That's the only way for the net. So we need a charge to be minus 2 value. And then what about
this angle is actually the angle between the resultant vector and the x-axis.
Think about
theta here, or sorry, the angle between the x-prime axis and force 1 is 10 degrees.
Welcome to EDU World Space.
20 degrees and F1 forms.
Okay, so we have two concentric spherical shells in a radius A, outer radius B of our inner shell, and radius C, outer radius D of their outer shell. The inner shell has a total charge of plus 2Q, the outer shell has a total charge of minus 2Q, so we're going to find the electric field everywhere, and where the charges are. So let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K
In this problem,
equals 9
I just draw the free body
times 10
diagram.
to the 9.
Now, here
It's also
theta is the
equal
angle made by the force F with the
1
horizontal in the
over
anti-clockwise direction and FR is the resultant force.
Epsilon is just a constant.
And phi is the inclination of
Also
resultant
remember
force with
Gauss
positive
law.
x-axis in the counterclockwise direction and alpha is the angle made by the resultant force with
Says that the
negative
closed
x-axis. Now I
integral
will
of E
apply
dot
the
A equals
law
Q,
of
the
cosine
charge enclosed divided by epsilon.
the vector triangle
Alright, so
and
first
the
region,
expression for
radius
slope
less than A.
square
Okay?
is equal to
We are
AB
here,
square
green
plus
dot. We have no
OB square
charge there,
minus
so
Q
the charge
multiplication
Q is 0. It's
AB
also
multiplication of OB cos angle is
okay, A less than R less than B, just a constant. We're in this
can write the next expression as or
This is
A equal to under
conductor for the properties and
AB square plus OB square minus is B multiplication OB multiplication cos angle AB cubed. And finally you can write the value of FR as under 450 square plus 700 square minus B multiplication 450 multiplication 700 multiplication cos 45 degree. So you will get the value of FR as
4 pi epsilon
497 Newton. This is the magnitude of resultant. Now applying sine over root to the vector triangle, so I can write OA by OB multiplied sine angle
C less than
AB by
C less than or equal to
AB by sine angle is
what is the total charge in here?
FR by
Must be 0. What is that?
FR by sine angle
So
AB is equal to 450 by sine angle.
now what happens if you're outside of it? So now what
Substituting the value, so you can write 497 by sine 25 degree is equal to 450 by sine AB by 15 degree plus alpha or 15 degree plus alpha is equal to sine inverse 450 by 497 multiplication sine 45 degree by sine. So finally you can write the value of alpha as
Now let's look at where these charges might be.
39.81 degree minus 9 degree, which is approximately equal to sine 25 degrees. Phi angle is equal to 180 degree minus alpha, which is equal to 180 degree minus 25 degree. So you will get this value as 155 degree. The inclination of resultant force with positive x-axis in counterclockwise direction is 155 degree. So finally you can get the value of alpha as 9.81.
Question 47. Wow, it's the same question. So this time we're told that F sub B is 600 newtons and theta is 20 degrees. This is the same question but actually easier. It's kind of like we're working forwards on this one. Question 47. Same question. Given basically everything we need to know. So the sub B, straightforward. This is the point. And magnitude and direction of the result. So F our X is going to be 700 sine 30 minus 600 Is it 20 degrees? It is 20 degrees. Cosine 20. F-R-Y is add them both together. 700 cosine 30 plus 600 sine 20. 600 sine. Yep. FR is the square root of FRX squared plus FRY squared. So let's just put those into the calculator.
So,
in parentheses, 700 sine 30 minus 600 cosine 20 squared sine equals in parentheses 700 cosine 30 plus 600 sine 20 and square it.
And this is how
839 in the calculator. Now this is question 47. That is the correct answer. And now inverse tangent sine 30.
So 400
the y value over the x value. 700 sine 30 that in the calculator. Plus 600 and squared.
Alright, what about in between A and B? Well,
let's extinguish the other equation. That is the correct answer.
By definition.
And now, inverse. See how am I measuring this?
0.
Counterclockwise. From the positive y-axis. Interesting. Think about what's going on here. FRX is negative 213.
Now we do have some charge. The total cost of the shell was 2Q.
FRY,
just in general, we have measuring this
counterclockwise. 811.
K, which is 1 over 4, KQ.
Interesting.
Squared.
Think about what's going on here. So the result would be here. So the theta that I measured is this, and I calculated is that, and that theta was 75 degrees.
Right here,
negative, but it means that 75 degrees. So we're going to measure it counterclockwise from the positive y-axis, and that's going to make it there. So that's just going to be 15 degrees. And that is correct. This.
Now we're about to region C.
So theta was the resultant here.
Outer ring. Remember that the field must be 75 degrees. So for the region C and D, E equals 0.
And that is correct.
Okay. And then finally, what about if we are outside of this area? So what about So we just said this formula right here for particular charge, and we get electric field E, yes, F1 equals 1 divided by 5.
Looks like it is.
6Q. These are all versions. So if we wanted to graph it, we could complete this. And we have R, and we're given, and we have 1A, B,
So my plane, the right angle here,
and we are going to get
here, B. This is 40.
And what about between C and D?
This is 30.
Originally, 0 inside of and between regions B and C. So it goes as a 1 over R squared.
Okay, so let's go ahead and resolve
And
F1 is just
we see a similar function for X and R D.
F2.
However, this time we are going to have a prefactor
So
and it's going to be
XY plane is going to be
and so that's that. Now, what about the charges on the
third degree?
So, because
F2 in the X direction.
well,
Positive.
okay, so the
and then that's going to be the sine of 40.
0. Why is that? Because the electric field is 0 and we have a Gaussian surface. So this guy is surface. Just see the charge right there. This is the inside. What is that?
Only
Inner.
it's still in the positive y direction. Positive y
is 0.
It's going positive x. In the z direction, it's going negative y.
Negative of the outer.
And that's going to be the sine.
All the outer surface right here needs to contain all the charge for this inner shell. So it has to be equals to Q. Okay. And what about for our large?
And then you need to add that to F3. The result is positive y-axis. Alright. So F1x
all the outer surface.
F2x.
So we get the Gaussian surface right here.
Zero.
We know that we must have a net 0 electric field to Q. The only way for that to happen is that there must be an induced negative 2Q charge inside of it. So it has to be negative 2Q. Why is that? Because the net
Put F3x down, alright. So
outer
there's
surface.
negative in the direction.
The Gaussian surface.
Okay. So
That's just the total charge.
F3 is going to equal F1 opposite.
And that's that. If that happens, there must be. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be
In the y direction,
taller.
what the result is.
Because this is 6 divided by 4 is 5, and this is 2. So this is how to check charge.
F3y.
And that's that.
Times equal F1. So F3y is going to be 600 minus F1.
This is
Minus
what type of units
to EDU World Space.
Plus 3z zero. So F3 is at the top is F1z plus So let's go ahead and calculate those. Wish you could see my calculator, but it just slows down my computer way too much to have it be recorded. So I'll tell you what I'm doing. So I'm going to do F3x, so it's going to be negative parentheses F1x is negative 180. Yeah, I forgot, F1 we had one. Plus F2x. F2x. F2, 300, way too much. Cosine of 30. So, sine 40. That gives me 13 negative parentheses. F1x. Negative 138. Opposite that plus that. Okay. So F3y is going to be 600 minus F1y, which is 0. Cosine minus F2y, or F2y, F2, 1300. 100 times cosine 30, cosine should be 40. Okay. So F3y is going to 40. That would be 401. 401. Minus. Okay, F3z is just going to be the opposite of F2z. So F2z 30 is negative, so the opposite of a negative is positive, so F2 300 times would be 400. So I see that they're all in a positive direction. Interesting. Wait a minute. So wait a minute. Yeah, that makes sense. Opposite negative positive, so F2. Okay. Determine the magnitude and coordinate direction of F3. So now I need the magnitude of F3. Square root of F. So squared plus F. Y squared plus F3z squared. So let me put that into the calculator. Square root of this. Okay. Determine the magnitude and coordinate direction of F3. So I need the magnitude of F3 squared. Square root of F plus this squared plus F3 squared. So let me put that plus into the calculator.
Outer surface and the surface area of the outer surface of the shell. Now in the next part we have to draw the electric field lines within the shell. We know that the electric field lines emerge outwards from the plus Q charge. So, in this region where R is less than A, the electric field lines are as shown in the diagram. These lines are emerging outwards. And minus 2Q charge is negative, so electric field lines point towards this charge. So in the outer region of the shell, the electric field lines are towards the shell. In the last part of the question, we have to draw electric field versus the radius of the shell. On the x-axis we take the radius, and on the y-axis we take the electric field. We can draw the electric field as the electric field becomes 0 at A, remains 0 in the conductor, and suddenly rises at R greater than B. This is a required graph for the electric field.